Okay, start recording. We're recording. Hello, YouTube. This is the second time I'm recording this intro because I had music earlier and we can't put music on YouTube. So, Raytracing in a weekend, day 2. This is actually the day after. We're still on time to finish it in a weekend as, as God intended. We did a bunch of math. Most of it was okay. Some of it I didn't get, but I guess it's fine. There was a bunch of C++ stuff at some point. We skipped all of it because it's insane and we don't have to do any of that stuff in reality. If you watch the VOD, you will see that you can actually do a lot of stuff without shared pointers, without abstract classes. None of that improves anything. Actually, it makes everything more confused. And we're at 6.8, which we need to start. And it says that it's an interval class, so there's more C++ stuff ahead. But I think we're going to be able to survive. So 6.8. Okay, let's go. Let's see. Before we continue, we'll implement an interval class to manage real-valued intervals with a minimum and a maximum. We'll end up using this class quite often as we proceed. So this is another class. I'm going to make a struct for this. So I'm trusting that it's worth creating a struct for an interval. I don't know that for sure. I'm starting to become a little bit suspicious of abstractions created by the author. That said, interval as a struct, it doesn't seem too bad. Thankfully, interval doesn't inherit from hitable, at least. So, because yesterday we saw how we created like a class that contains a vector of objects. By the way, the book wasn't able to call objects. They had to call them hitables because object is already taken in an object-oriented world. Zig is not an object-oriented world. So for us, objects are actual objects. That's nice. In any case, we need interval. So where do we put interval? I'm going to put it under objects. I'm not sure if it's the right place, but it seems reasonable. So pub_const interval struct. I guess there's, what do they call the fields? Min and max. Okay, so there's a constructor that creates an empty interval. Man, this is not only empty, it's also like very big in its emptiness, as in minimum is plus infinity, maximum is minus infinity. So it's, yeah, it's empty for sure. That's interesting. They could have picked something different than just infinity, I guess. Do they do anything special with infinity in this case? Oh, maybe it makes comparisons easier. I don't know. In any case, fine. We're going to replicate this. So min and max. F64. Max. Pub function init. We need init. You know what? We can just do... so max by default is std.math. And I don't know, inf. Yeah, float.inf. Is it a function? Yeah, it's a function once the type. Is there like negative inf, or are we just negating the inf? I guess we can just negate the inf, right? So let's do that. Also, you know what? Yeah, I think Andrew has a good point. Deck literals time. Yeah, maybe we don't need to give it default values. Let's just create a decal for it. Yeah, pub const empty equals min equals. Let's import. Should we import inf const inf 64 is std.math.inf for f64. There we go. So min is inf64, max is minus inf64, and this is our empty interval. Okay, what else do we have to offer? Size. Well, let's copy everything else that we want to offer. Static const interval empty comma universe. I have no idea what this last thing is supposed to say. Does any C++ fetishist know what that means? Size, F64, return. It's constants in class namespace. It's the same as your empty. Oh, okay, cool. Okay, so we have size, then we need contains. You know what? I'm gonna repurpose this. Function contains x f64 returns a boolean, I think. There you go. Then surrounds contains surrounds. It's the same except not the extremes. Okay. 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 So we have it. Then oh, there we go. Oh, I see. Universe. Oh, okay, I get it. So they define the class in here. Then outside they define two instances of that class. And then, which is available in the file, but it's not publicly available, I guess, and they don't want to do that. But then these guys are made available as what was it, static decals, as like decals namespace inside an interval. Sure, the point is universe is the opposite of empty. Universe is from minus infinity to plus infinity. So I guess we can have universe. Okay, we have it. Why is everything so needlessly complicated in C++? I don't know. There's certainly like a love for, I don't know, hermeticism in a sense. Also, well, you know what? Let me put it this way. I do think that it's actually normal and good that, you know, I don't know, 40 years after C++ was created, we can look at it and say, yeah, we can do better. Honestly, I'm hopeful that 40 years from now, somebody can look at Zig and say, yeah, this language got some things right, but also, oh man, look at these things. Now we know how we can do better. I honestly hope that keeps happening, because otherwise, I don't know, it means that humanity kind of stalled. So we'll see. That said, I might be too optimistic. We'll see. Someone writes Zig++. Oh god. So interval, what's happening? Oh, we're changing the abstract class. So we're changing the signature of heat from accepting two arguments to only one. I have to say one thing. I would not hate if this syntax was like if these code snippets were actually proper diffs. It's a weird in between not offering a proper diff and only offering the updated code snippet with the change lines highlighted. It's a choice. I get it. But anyway. So we want to go into, I think it's objects, right? So it's heat. We want to change from tmin to tmax. What is it? Ray interval? No, ray t is the interval. Why do they call it ray t? I'm just going to call it interval, I guess. There we go. And then what interval? Yeah, I mean, it's relative to the ray. So I would understand ray interval, but ray t? I don't know why t. I don't know. I'm just going to call it interval. So here we have hit everything to do. Now we have to change what we pass down, right? So this needs to become an interval. And then here I'm guessing it's using maybe a function for any of this stuff. No. So here we change not. Oh, this is the hittable list. Okay, the hittable list doesn't really change anything except that closest so far starts. Right, closest so far starts at. What is this? Ray t.max. Oh, because it was passed in while we're not passing it in. So this actually stays the same for us. Then let's look at object. Maybe something changes, well, in the sphere. Maybe something changes in the sphere because I feel like some of the stuff we have just implemented, right? So let's just see what this does. Yeah, the outer if becomes not surrounds and the inner becomes not surrounds. Okay, so in theory, we shouldn't have broken anything. I think this can go on the same line. It's fine. And then ray color passes 0 infinity, but yeah, we're not doing this in our implementation either. Let's see, you remove the interval arguments, less stream. You use constant directly and hit everything. Yes. Okay, so in theory, this refactoring shouldn't have broken anything. Let's see if this is true. And it seems fine, and our image is fine, so we're good. Okay. Moving camera code into its own class. Oh god. Okay. Before continuing, now it's a good time. Now it's a good time to consolidate our camera and scene render code into a single new class, the camera class. The camera class will be responsible for 2 important jobs. No! God damn it! One class only does one job. It's the single responsibility principle, man. Your code is not clean. What is this dirty stuff that you're making me do? God damn it. Let's see. Construct and dispatch arrays into the world. That makes sense. So this is the process that I guess this is in a sense the main process that we've been building, right? So the idea that we sample the space by creating arrays that originate from the camera and go and sample what's in front of it at regular intervals to sample what the pixels should be at a given location, and then we construct in a sense, we kind of construct a. Oh man, what do you call that thing where you're making an image out of tiny pebbles? What do you guys call this thing? By the way, I think it's the same term that we use also in Italian. I'm just having a huge brain fart right now. Mosaic. We're making a mosaic. That's kind of what we're doing. We are basically building a mosaic of the space, and it's just that our pebbles are small enough. Okay, use the results of these arrays to construct the rendered image. Yes. In this refactoring, we'll collect the ray color function along with the image, camera, and render sections of our main program. The new camera class will contain 2 public methods, initialize and render, plus 2 private helpers methods, getRay and rayColor. Ultimately, the camera will follow the simplest usage pattern that we could think of. It will be default constructed, no arguments. Then the owning code will modify the camera's public variables through simple assignment. And finally, everything is initialized by a call to the initialize function. This pattern is chosen instead of the owner calling a constructor with a ton of parameters, or by defining a calling a bunch of setter methods. Thank you. Thank you. Thank you, Raytracing son. Thank you. Look, we could have tortured you more, but we're not going to do it this time. Thank you. Thank you. Instead, the owning code only needs to set what it explicitly cares about. Finally, we could either have the owning code call initialize, or just have the camera call this function automatically at the start of render. We'll use the second approach. Why? I mean, if you're calling render only once per execution, then fine. Why are we spending a paragraph talking about this stuff? Anyway, fine. After main creates a camera and sets default values, it will call the render method. The render method will prepare the camera for rendering and then execute the render loop. Here's the skeleton of our new camera class. Let's go make this camera. So I'm going to make a new file. I'm going to write it in source/camera. Note the uppercase name because we're making a file struct. So const camera equals this. Do we need std? We probably need std. Then what does it need to have? I mean, we'll see the parameters. We're set pub function init, and then pub function render. Render takes a camera, probably with a pointer. We'll see. And I don't know if it returns anything. Probably not. Init gives us a camera. Okay. Okay. Initialize, and it has ray color in it. Well, I guess I'm just gonna move ray color inside. Is camera hittable? Good question. Let me think about it. Technically, yes. Camera should be hittable if you think about it. Maybe this is explained in the book, but if you think about it, when you're rendering a... okay, I'll take this back. No, it depends on what you're doing. But if you're rendering something from the POV of a object, then that object will in turn reflect some of the light that it gets hit by onto other things in front of it. So if you want to have, for example, a mirror and the camera is, you know, a guy, you want to see the guy reflected in the mirror surface in front of it. So that means the camera should be hittable? Maybe? Maybe not. I don't know. You know what? Also, I don't know clean code. I think this is a question that only clean code can really answer if we really think about it. Okay, so recolor goes inside. Also, initialize is private, apparently. That's interesting. We don't even get to see what the fields are supposed to be. This is ray color. Wait, is this different than before? Is it the same? It's the same, right? I will assume that it's the same and nothing has changed. Now we move almost everything from main into the camera class. The only thing remaining in main function is the world construction. Here's the camera class with the newly migrated code. So we have inside of it aspect ratio, image width, and in render we call initialize. What does initialize do? This is so cute. Initialize runs the math that should run at comp time. Oh no. Oh no. Well, so we don't need init. Also, how many cameras are we gonna have? We're only gonna have one camera. Now that I think about it, if we're only gonna have one camera, we don't really need it to have an uppercase name. Let me do this. Move source. So here's the problem. I'm on a file system that has, this is a case insensitive file system. And I might be wrong, but I believe that if I were right now to name camera, rename it to lowercase camera, it wouldn't work. I need to move it to something else. And then I need to move it back to camera with a lowercase name. And so now we don't need this because it's, in a sense, it's a singleton. And because it's a singleton, we don't need struct like fields. We can have decals just like we had before. And they're global values and it's fine. They basically are just namespaced. That's the only difference. And this is perfectly fine. Like there's literally nothing wrong with this. So this is fine. They're private. They're not public. So these are not accessible from the outside. Maybe we should make them accessible. We'll see. But so far, so good. Render doesn't need a camera parameter because we are basically just accessing these values. This whole work that we're doing, some of it makes sense. Some of it, like what I'm doing right now is what we actually want to happen. This fact that we are creating something that you can create instance of in here does kind of seem sus. I might be wrong. Maybe in the future we'll create more than one camera. But for now, it doesn't seem like that we're doing this. If we ever do, then I'll do the work to refactor everything into something that you can make multiple instances of. In any case, so initialize, we don't need initialize. That's this is cringe. So we don't have this. Oh yeah, those are private fields, so they're not meant to be accessible from the outside. Aspect ratio and image width are supposed to be public. So let's go make those things public. It's pretty common for games to have multiple cameras. Cool. Okay, and so in render we have basically the printing code. Okay. So from here to about out. I guess we should accept out as a parameter here. Oh, sorry for the noise. Okay, there was an ambulance passing by. I don't know if you guys could hear that. Out is is a writer. Man, I got so good at typing const writer equals stdio writer. It's like I'm never gonna forget how to do that. I think we can even take this out. Do we even need Ray? Maybe we do. Let's keep it for now. Okay, hit everything. So we want to move down, hit everything as well. There we go. And then, oh, we're doing the progress start stuff. Do we do it outside? I think the progress we can put in render. For now, at least, we'll see. Okay, next problem. Pbuff. Coming with me. World. I'm guessing you pass it in. camera.render. Oh, there might be tries in there, so this needs to be able to return an error. We need to try this out. World. I think this is it. Does it work? Yeah, okay, we have successfully refactored. Actually, let me remove this file just to double check that we do create it. No, it works because it's in the CLI that we do this, so it would be empty if something failed. Okay, so far so good. We did all of this. Let's see, so main has, yeah, creation of the world, creation of the camera. We do specify here aspect ratio and image width. And that's fine. Well, you know what? We don't do it here, but I'm going to move it if we really have to. So far, it seems fine. Okay, anti-aliasing. If you zoom into the render images so far, you may notice the harsh stair-step nature of edges in our render images. Yeah, definitely. The stair-stepping is commonly referred to as aliasing or jaggies. Jaggies? When a real camera takes a picture, there are usually no jaggies along edges because the edge pixels are a blend of some foreground and some background. Consider that unlike our rendered images, oh wait, I know what's happening here. We have just created a, in the interval we have surround and what is the other one? Contains, which makes a distinction about the edge case. Although, this is gonna be interesting because it's in objects, right? Yeah, I put it in objects. So yeah, we made a distinction about the edge case. That said, do we really hit the edge case with floats? That seems this seems kind of thin, right? Like the equality extra condition seems very thin. I guess we'll see. So my wonder right now is, are we going now to make a distinction in objects sphere heat? Where is it? Are we going to make a distinction between surrounding and containing? And are we going to do some magic? Or I think we'll have to do maybe something like this. But maybe we need better control over the epsilons. Like the tiny deltas, than just that. We'll see. Okay. In any case, consider that unlike render images, a true image of the world is continuous. Put another way, the world and any true image of it. What even is a true image? I guess you could say that a true image of the world is the perfect C++ class. When you really make a C++ class that truly inherits from the right thing, that truly contains the right behavior given its name, and you really perfectly decide what the default initializations are, what the constructors are, when you truly perfectly define when a method should be public or private, or static or const, or override, or I don't know, only then you will have created a true image of the world. Anyway, sorry. Let's see, as effectively infinite resolution, we can get the same effect by averaging a bunch of samples for each pixel. Okay. Oh, so we are ray tracing a lot more now, I guess. Oh yeah, so within a delta, we are sampling, we're sampling more, and I'm guessing we're averaging the sampling. That makes sense. Okay. So long story short, no, I was right. The difference between contains and surrounds is not manageable. You need to sample. You need to sample within the pebble. And I'm defining a pebble as in, you know, the tiny square. We saw this stuff. It's the image with delta that goes down and the delta that goes right. Those are the pebbles, basically. Okay, so with a single ray through the center of each pixel, we are performing what is commonly called point sampling. The problem with point sampling can be illustrated by rendering a small checkboard far away. If this checkboard consists of a 8x8 grid of black and white tiles, but only 4 rays hit it, then all 4 rays might intersect only white tiles, only blacks, some with an odd combination. In the real world, when we perceive a checkboard far away with our eyes, we perceive it as a gray color instead of sharp points of black and white. That's because our eyes are naturally doing what we want our ray tracer to do: integrate the continuous function of light falling in a particular discrete region of our rendered image. I mean, yeah, I guess ideally we would want this, but then we just do sampling. Clearly, we don't gain anything by just resampling the same ray through the pixel center multiple times. We just get the same result each time. So what we want to do is sample the light falling around the pixel and then integrate those samples to approximate the true colors result. So how do we integrate the light falling around the pixel? We'll adopt the simplest model, sampling the square region center of the pixel that extends halfway to each of the 4 neighboring pixels. Yes, this is not the optimal approach. Oh, but it is the most straightforward. See, a pixel is not a little square for a deeper dive into this topic. Okay. Oh, it's a paper. Cloudflare-san, please allow me to see the paper. A pixel is not a little square. A pixel is not a little square. A pixel is not a little square. And a voxel is not a little cube. Okay. Cool. Maybe we should do the same. Asynchrony is not concurrency. Asynchrony is not concurrency. Asynchrony is not concurrency. And concurrency is not parallelism. Cool. Well, I'm not going to read this now, but this seems interesting. Cool. I'm actually going to check this later on my own, I think. Okay. So let's see. Some random number utilities. We're going to need some random double in range. Okay. We have this in the standard library. And before chat asks, no, random is not hitable for now. C++ did not traditionally have a standard random number generator, but newer versions of C++ have addressed this with the random header. Okay. Yeah, like we don't care about this. I'm going to do the right thing in Zig when the time comes. Let's see. Generating pixels with multiple samples. For a single pixel composed of multiple samples, we'll select samples from the area surrounding the pixel and average the resulting light color values together. Yeah, so this is kind of a, let's say, it's a Monte Carlo approach, basically, to finding out what the given pixels should look like. That seems fair. First, we'll update the right color function to account for the number of samples we use. We need to find the average across all of the samples that we take. To do this, we'll add the full color from each iteration and finish it with a single division by the number of samples at the end before writing out the color. To ensure that the color components of the final result remain within the proper 0.1 bounds, we'll add and use a small helper function, interval clamp. Clamp double X. Oh. The random double with range is actually not in the standard library. Interesting. We have a std math clamp. Okay. But I'm not sure right now why we need clamp, because, well, you know what? I'm gonna wait a little bit more until I see usage code. I want to see usage code of this clamp. Right now, I'm slightly not convinced. Let's see. Here's the updated right color function that incorporates the interval clamping function. Let's see. Right color, translate the 0, 1 component values to the range 0 to 55. Static const interval intensity. Wait a second. Where's these intensity stuff? Now I'm forgetting. We're looking at vec, right? And we are doing the color printing. And we're doing intensity clamp. Okay, so the point, okay, I get it. So the point is, we're not sure anymore they will get to right color with these values R, G, and B contained within 0 and 1. They might fall outside of it. They might fall outside as the result of our sampling. That I find suspicious. I'm not sure. We'll see. But then what they're saying is, if we do fall outside, then we clamp. And I guess that's when you basically are clipping in cameras, right? When something is too, the light of something is too intense, you clip and it becomes white. Although that is not a software clamping, I believe that is also physical limitation of the tool. But okay, so I want to see us produce RG and B that goes outside that range, though. I want to see that, and then I'm gonna do this stuff. Now let's update the camera class to define and use a new camera get ray ij function, which will generate different samples for each pixel. This function will use a new helper function, sample square, that generates a random sample point within the unit square centered at the origin. We then transform the random sample from this ideal square to the particular pixel we're currently sampling. Yeah, so we're getting a... Yeah, that makes sense. So we're choosing a random point in a unit square, and then, quote unquote, we shift it to the actual coordinates in the image that we're trying to sample. Yeah. Samples per pixel. Oh, now we're getting there. Oh man, now we're finally. Oh, you know what? I'm really happy because we're finally starting to the point where performance starts to matter, and we can kind of flex on the C++ implementation, I guess. So who does what? Let's see. Camera also has the concept of samples per pixel. Sounds good. So samples per pixel equals 10, we said. Then in render, in the inner loop, I guess I'm going to copy this. So in the inner loop, is this the actual full content? Yeah, this is the full content of the inner loop. So we need to replace pretty much everything with this. So what are we doing? We start with a pixel color set to 0. So this is like the var pixel, basically. Var pixel for us. And it's a vec 3. And we can start with 0. Then, so this is this. Then we have a for loop. Now we have one more for loop that we didn't have before. And this is for each sample. Int sample equals 0, sample lower than samples in per pixel. Okay, so for us, that's 0 ... samples per pixel. And I don't know, I'm going to call it S for sample. And then we get an array for each one of these guys. Okay. What were we doing before with the array? Oh, we were just instantiating it ourselves. So now we're going to make something else. Isn't S a sphere? In other contexts, yes, it's a sphere. But in this context, we don't care, because in this context, we don't deal with the sphere specifically. We only deal with the world. So we only basically then call ray color with a given ray. This maybe is going to change a little bit. Oh no, we're still going to do pretty much the same. So we just do ray color with a given ray and the world. And then in here, Well, in hit everything more specifically, this is where we start like touching the sphere, but even then we just call it obj. So it's fine. In this context, there's no confusion that here S is sample and not a sphere. Okay, so we get array. Maybe we can make it a method of ray. Do they make it a method of ray? Where do they put this stuff? Get ray. Oh, what? The get ray is not a thing of ray. It's of camera. It actually makes sense because it uses a bunch of properties of camera. That's fine. I was about to make an OP joke. You know, oh no, you gave the method to the wrong object and now... anyway, sure. So we do... get ray. I comma j, so w comma h in my case. And then we add this stuff to pixel. Yeah, pixel plus equals ray color of our world. That makes sense. And then we need to divide by the number of samples, right? So we need to do pixel divide equals vec.splat of samples per pixel. And here we have right color. Yeah, which is the printf at the end. So I think this pixel center stuff goes into get ray because that's what what uses W and H. So I'm keeping it. I'm not deleting it. I'm keeping it around because we're gonna use it. Ray direction. I think basically this stuff is all going into that function. Okay, so I think this is it. Do we have the division here, or did I just make it up? Make it myself? Samples per pixel. Pixel samples scale. Wait. Why is it like this? Am I missing something? Why do they create a new field for the inverse of pixel samples per pixel? What even is the point? And then they multiply here as they print. Why don't you just do this? Am I missing something? Anyway, let's do get ray. And this is where we're gonna need some randomization, right? Some random noise. Construct a gamma ray originating from the origin and directed at randomly sampled point around the pixel location ij. So let's see, sample square. Sample square, and then pixel sample is pixel 00 location plus I. You don't want to do division in a hot path, but you can just put it outside for look, and it will be fine. But wait, wouldn't any optimizer that, you know, it's not turbo dumb understand that if you are dividing by a constant, you compute the inverse of the constant once and then you turn this into a multiplication? Like, I would assume that this is like optimizer 101. And you should trust it to be able to do that right. You know what? We can benchmark this, I guess. We can see how this behaves that way, and then we can write the other version and see if it's any better. To be fair though, I understand programming a little bit defensively with regards to this stuff. Still though, this seems so basic that I don't see why it would be any different. Also, this is not this. This is actually nothing. Yeah. Okay. So let's implement getRay. Okay, let me think if I would implement getRay in a different way. I'm worried about LVM just computing the final image at compile time. I don't think it will. It gives up way earlier. There was like an example. Andrew, go look for the thread on Zigit about assert. Oh, there's actually also a blog post. I can link the blog post. Like, take a look at this blog post by CryptoCode. Look at how early LVM gives up. So I think that we want basically. So the problem is we do want to add some noise, but yeah, we need to compute the noise first and then let's see. Okay, sample square returns the vector to a random point in the -5 plus, sorry, -0.5 -0.5 plus 0.5 plus 0.5 unit square. Yes, so this is your sample square. And then they call it offset. And then they do pixel location plus I and j plus the tiny offset multiplied by pixel delta u and v. Yeah. So you need to do the addition before doing that. But also, this seems a little bit, you could pull this off with just doing the generating two random numbers and adding them in here without making a vector for it first. But fine, let's do it this way. Maybe there's going to be we're going to add some sophistication later, and this structure helps with that. I don't know. I am starting to get suspicious though. Sample square. Let's make a sample square. Which actually returns a vec3. Yeah, with z set to 0. Yeah. Okay, so oh, we already have std actually. But we want to probably. So how do we do with the random state? I'm gonna put it out here for now, maybe. Then if we need it somewhere else, I guess we can worry about it later. So const rand equals I think it's rand state. std. Oh, you know what? We might have already some state initialized for us in the standard library. Let's take a look. Rand random. What? Oh, wait. It's uppercase random. Okay, uppercase random. Then we have default PRNG, which I think that's what we're going to use. We're going to use Soroshiro. By the way, you know what's funny? I might be wrong, but I believe that Soroshiro, despite the name, it's from Milan. It's from the University of Milan. It was made by people in Milan. Soroshift. Soroshift, but Soroshiro, I guess it's based on this, but it's a specific thing. So, yeah. Anyway, funny minor anecdote. Okay, so Soroshiro needs some state. Yeah, we're making an instance of it, so there's no There's no free instance for us in here, is there? Let's see. Oh, we can do init. This is the random interface, is it? Let's see. Pointer field function. Yeah, this is the interface. This is the random interface. Okay. You know what? I'm gonna put this random stuff. Yeah, exactly next to where we use it. So std.random default prng.init. We started at 42, of course. And then this needs to be var. Then here we do const rand equals rand state dot random. Is this a function? It is a function. Perfect. Then we do, okay, so next we need to make a vector. I'm going to copy this. So okay, random double minus 0.05. Yeah, so this is rand dot float. Nice. Return a random f64 evenly distributed within the range 0, 1. Yes. Thank you. And then we do it again, and that's it. I think we can actually fit this on a single line. You know what? I prefer this, I think. Okay. So we have a sample square. And then we make one, and then we sum it. Is this a mul add? This is not a mul add. This would be a add mul. Do we have add mul? Vector splat w. So offset equals sample square plus offset. Wait a second. Are we doing this correctly? I plus offset x times pixel delta u pixel delta v. Yeah, this works because this guy has 0 as the last thing, I believe. So okay, plus offset dot now we can't do we have to do back dot x of offset and plus back dot y offset. I think this is it. Then let's see. Ray origin equals center. Ray origin equals center. I think we... Wait a second. Oh, wait. This is the pixel sample. This is not the pixel center. This is pixel sample. Okay. Then ray origin equals center. What is center? I lost center. Center is the camera center. Okay. Do we have it up here? Center somehow? Camera center? Camera center. Okay. Oh, it's back to 0. of course. Yeah. Oh, so we. What? Sure, sure, sure. Okay, and then make array out of this. Okay, so we should be doing everything. So this is pixel sample. There you go. Okay, next error. What's happening? Unused capture. You're right. The number of the sample isn't really a factor in what we're doing here. Okay. Do we work? No. Type vector 364 has no members. Back dot zero. There we go. Incompatible types use size and F64. There we go. Incompatible types. So this needs to become float from int. Oh no. Oh no. It's not gonna work. Okay, we don't do this. Here's how we do it. Now we don't need to do that. We can do this. Okay. Yo, I was about to say it's still fine. It's not just fine. Look at it. It's also smooth. Smooth. Actually, not terribly smooth. But what if instead of 10 samples, we did like 100 samples? Okay, that was slower, but not horribly. We didn't gain much. The problem is that we don't have a super high resolution. We will need a much bigger resolution. Let's say that we keep actually like 10 samples and then the image is just a little bit bigger. How would that work? Also, by the way, here's what we're gonna do now. Yeah, we're doing zbuild run, but now we're doing -o release fast. Unrecognized argument. You're right. It's -- release equals fast. Okay. Yeah, that's what I'm talking about. That's the good stuff. That's the good stuff, man. That is the good stuff. Okay. Maybe I should set it back to what it was before. We need something better for the progress. You know what? Let's do 4,000. I want to see this go slow so we can test our progress bar a little bit. Let's say that we do 1,000 samples per pixels, okay? So let's watch it run slowly. You see how it's not making progress? It's because we're not really using progress as we should. So this is height times width. Let's just do height. And let's just do it here. So we do PR dot. Actually, I don't know what you can call on nodes. What do you call on nodes? Start. Set byte swap. No, none of this stuff. Where is it? Start. Okay, you call start on it. And then you call complete one. Oh, no, we can call complete one, I think, on the parent directly, right? We don't need to start a new one. Let's try. Yeah, there we go. Now we see the progress. We could be more granular. Like we could, for example, count also the number of samples. We could count like every single operation as a unit of work, and then we could also show progress based on that. But honestly, this is fine. It's working. Yeah, man, it doesn't take much, huh, to make this computationally turbo expensive. So what do we want to do here? Let me think. The release fast argument isn't being passed to Zig build. You don't think so? It seems it is. I mean, this seems to be as fast as it was a moment ago. It doesn't seem significantly faster. Look, I'm doing what chat is complaining about just to show it. We can also add a print, you know. Let's go in main and let's say let's talk about our debug mode. There you go. By the way, it's just that I gave like very very evil numbers, like 1,000 samples per pixel, 4,000 pixels. You know, it's a lot of work. Like if we go to something more nice, it doesn't take that much. Okay. So in any case, we tested our progress report, which is good. Let's see. In addition to the new sample square function above, you will also find the function sample disk in the GitHub source code. This is included in case you would like to experiment with non-square pixels, but we won't be using it in this book. Sample disk depends on the function random in unit disk, which is defined later on. Okay, so I'm guessing this has to do with the book, where the idea is that instead of sampling on a square, you sample in a circle, and that gives you better properties. Which is, I guess, fair. So, oh, you wanted to see the Super Turbo one, but I think it's already pretty much as good as you can see in this on this screen. Zooming into the image that is produced, we can see the difference in edge pixels. Yeah, we definitely saw that. Diffuse materials. Oh, there we go. Now that we have objects and multiple rays per pixel, we can make some realistic looking materials. We'll start with diffuse materials, also called, how do you guys pronounce this? Matte? Matte? I guess matte. One question is whether we mix and match the geometry and materials so that we can assign a material to multiple spheres or vice versa. Or if geometry and materials are tightly bound, which could be useful for procedural objects where the geometry and materials are linked. We'll go with separate. Man, this is I can already smell that this is gonna get us down some weird design decisions that are horribly influenced by C++ isms. Same as math. Okay, makes sense. Thank you. We'll go with separate, which is usual in most renderers, but do be aware that there are alternative approaches. Sure. Let's see. Diffuse objects that don't emit their own light merely take on the color of their surroundings, but they do modulate that with their own intrinsic color. Light that reflects off of a diffuse surface has its direction randomized. So if we send 3 rays into a crack between 2 diffuse surfaces, they will each have a different random behavior. I think that so far we have never bounced a ray on anything, right? We've only been projecting rays, and as soon as they hit an object, that's where it ends. And also when we compute intersections, we always, if for some reason we find a solution that is further away, we just discard it. So now I guess we have to do this. We kept the closest solution, and then we generate a new ray from there. We generate a new ray, and we can use the direction of the normal to know which direction the new ray should go towards, plus some randomness. And that's going to be the next step. And then we decide how many rounds of that we want to do. I'm starting to get it, I think. Let's see. They might also be absorbed rather than reflected. The darker the surface, the more likely the ray is absorbed. That's why it's dark. Really, any algorithm that randomizes direction will produce surfaces that look matte. Let's start with the most intuitive. A surface that randomly bounces a ray equally in all directions. For this material, a ray that hits the surface has an equal probability of bouncing in any direction away from the surface. Okay. This very intuitive material is the simplest kind of diffuse, and indeed, many of the first ray tracing papers use this diffuse method before adopting a more accurate method that we'll be implementing a little bit later. Ooh, there's a more accurate method that we will implement later. What would be based on, I guess, noise? So I'm guessing you don't, yeah, like things normally are not perfectly distributed. So I'm guessing there's going to be some, I'm guessing reflections are normally distributed. That's my guess. So the majority will follow. Will actually follow what? Let me think about it for a moment. I was mentioning the normal earlier, but it's not really the normal, the point, right? The point is the original vector reflected from that. That's probably what it's most realistic. Although, I don't know, I guess it depends really on the material. Okay, we'll see. Let's see. The first thing we need is the ability to generate arbitrary random vectors. Okay, so we're adding to vec3 a complete random vector, and then a random vector within min and max. Okay, let's go do this. So our vec3, well, our vec gains random. Where do we put it? Magnitude, splat, color, format, dot, cross, unit. I'm going to put it at the bottom. Our function random. You know what? I'm going to accept a random though. Like a random interface, which I think... is this an interface that I accept with a pointer or not? I don't remember. I don't think it is. Yeah, it's not a interface. It's not a pointer interface. Okay, so random. And I guess that's it. So we're returning back 3. And then random within a range. Random within a range, huh? What was this called? Right. It's still called random. It's just an overload. Of course. Why wouldn't it be? Random range and mean F64 max F64. Okay, how is this implemented? Don't we need hemisphere random? I don't know. So far, it seems that we don't. Float 64 times max minus mean plus mean. Yeah, that makes sense. That makes perfect sense. Thank you. Okay. Then it needs an assert that max is greater than. Yeah, you know what? Let's do it. Let's put the assert. Or we could do what the book wants us to do. If it's greater than, then we swap the arguments, return 0. I don't remember what it did in that thing. Our vectors, they're good. We made some progress. We have anti-aliasing now, and we're about to do diffusion. Yeah. Look, this is the kind of thing that the book was doing earlier. At some point, it doesn't know what an assertion is. You know what? Let's see. We're at 9.1. Okay, let's remember this. Let me go up. I'm gonna try to find it. At some point, it doesn't know what an assertion is, and so it does this weirdo defensive programming that makes no sense. What was it? We have an assert for it, so we can check for that. What are we asserting on? I think it's this, right? It's in the hit init. What other asserts we have? Sphere. Radius greater than 0. I don't think that was it. Oh no, yeah, that was it. I think it was the sphere. Like, what do we do with negative spheres? Search for Fmax. Okay. Yeah. So like there's a sphere constructor, and somehow they're worried that you give it a negative radius, and they say, look, if you give it a negative radius, then we make it 0. Why? And there's an explanation. Note that here we use the C++ standard function std fmax, which returns the maximum of the 2 floating point arguments. Similarly, we will later use fmin, which returns the minimum of 2 floating point arguments. And this is how they protect the code from negative radiuses. But how about you address the code where you are producing these negative radiuses? God damn it. What about infinite radius? Oh no, that one is fine, man. No, don't worry about that one. That one is cool. What about a nan radius? Oh, that one is also perfectly fine. Yeah, there we go. Also this. Set face normal. Note, the parameter outward normal is assumed to have unit length. Well, how about you assert for it? Man, you got me to use shared fucking pointers, then introduce me to std : assert. I actually don't know where asserts are in C++, but why do you just use it? Just put it in a comment. By the way, for us, in hit, we have in debug mode, we do actually compute the magnitude squared, and we check that it's close enough to 1. Fmax is 0, 9 is 0. Holy shit. I didn't know that. Also, what? Max between 0 and 9 is 0? No, you're joking. Actually, let me close the bottle because bad things could happen otherwise. NaN is not hammer, so it can be the max. Yeah, but usually the idea is that once you have a NaN in a computation, the NaN doesn't get thrown away. Like it's kind of like a float poison. That's how I understand NaN, and that seems to me the sane way of thinking about NaN. Like my expectation is that you don't throw away NaN because you're kind of throwing away the fact that you made a bogus computation, unless you have code that explicitly checks for NaN and then decides to throw it away. But like in a mathematical operation, I'm surprised that, like, if you do 5 plus NaN, I would expect it to be NaN. Let's test it out because it's blowing my mind. Does anybody remember where STDF max comes from? I guess you just need STD. Oh no, we don't have anything in here. Okay, how do we use this thing? Actually, no, you know what? I do want some zoom. Int square return, and then this computes it, but it doesn't run it, right? How do you run it? Main auto num equals 5. Are we good? Can we run it? Include CMath. Okay. How do you run stuff here? I want to see, actually, this shouldn't be a return, right? This should be print. Oh god, how do you print? It's the left shift stuff. Okay. Panic. Thank you. STD C out. Pixel samples plot. Oh wait, what is this? Oh, this is the other one. Thank you. Okay, I'll take a look at it in a second. STD C out. Yeah, but we don't have STD. Where do we get STD? Pound sign include CMath, and then pound sign include CDIO IO stream. It seems that it compiled. Program returned 0 and printed 25. Awesome. Awesome. We are getting there. So now we can take this out, and then we can do std : f max. But also, why do I need to import another thing to get something from std? Like, why am I including stuff and I don't even get a namespace for it? Not printing a new line. Sorry, let me shift left also a new line. Right, you're right. I forgot. I forgot to shift left a new line. So f max, and we give it 0. How do I get NaN? Oh, right, it's std handler. Okay. So how do I get NaN? Can I just do NaN? This is not gonna work, is it? Yeah. std : NaN. std in math NaN. There's no std math. Oh no, there is. Or there has not been declared. Okay. How do I get NaN? std : NaN. Okay. I was almost there. No caps? Okay, no caps. Is it so it's really NaN. No matching function for call. Uh, wait a second. For call fmax int double ampersand const char pointer. So well, okay, 0.0. Oh, it's a function. Wait, either you call the function or there's the wait. Why is the A also uppercase? What's going on? What is happening? Compilation failed. Too few arguments to none. It wants a char star. What? Expected unqualified ID before token. What is going on? 1.0 divided by 0 to generate none. Let's try. Warning. Division by 0. Program, it prints inf. It's a macro. So with division by 0, we are getting infinite. Oh, because this gives infinite, it doesn't give none. This is not giving us a none. We need a none. We need a proper none. Man, in JavaScript it's so easy. You just try to add the number to a string. 0 divided by 0. Thank you. That makes a lot more sense. Let's go. 0. Okay, what about this? Minus none. So fmax does throw away nuns. But what about fmin? It returns 0 again. Yeah, none can be signed. There's a ton of nuns because there's a ton of different patterns that are all nuns, and they like the standard sneaks in a bunch of meanings to all the various bit patterns for arbitrarity of reasons. I mean, wow, this is a thing, I guess. Okay, cool. You know what? Maybe this is how it's supposed to be. We are looking at what C++ is doing, but maybe what all they're doing is following the spec. You know what? I would be surprised if this is not following the spec. I would be really surprised. Okay, so let's look at this. Pixel sample is a vec3 that does dot mul add. Wait a second. This should be at mul add, right? Because we don't have mul add. Yeah, I think this is the built-in. Let's see. Mul add. I add the methods to vec3. Okay, so you have it there. Okay, so you splat exit of 0 pixel delta u. You think this is more efficient? You think that this would not be lowered this way without us doing it? Might be very well true, actually. I don't know. So this is in camera, right? Where did I go? This is not camera. Let's see if this works and we still get the normal image. Oh, wait, do we have? mole add. Oh, nice. Wait, was it add mole that I was saying? Do we have add mole? No, we don't. Okay. Expected fragments found 3. Type. Right. Back 3. Okay, let's see if we still get working math. I mean, almost, but this might be me. I think I've inverted W and H, yeah. Oops. There we go. That's nice. Let's try to raise these implementations. So we are doing sample, right? So to stress this more, we actually want more samples, and let's make 2 versions of it. So zig build run release fast. So this is not zig build run. This is zig build release fast, and then we are gonna move zig out /bin /Chris RTX to K1. And then we comment this out. We return to the other one. There might very well not be any difference, but I'm curious now. Zig build release fast, K2, and then hyperfine, K1, and K2. So K2 is the one without the mole add. Yeah, I could also have done the prefix. You're right. Oh, I went pretty hard with the number of samples. It takes 7 seconds to conclude one. Okay, well, I think it's fine though. Let's see if let's see how this goes. Yeah, I think I might overdid it. This is just K1, then we have to run K2, man. That takes a while. Okay, you know what? Let's not do this. Let's remove K1 and K2. Let's go a little bit, instead of 100, let's do 30 of these guys. Then we do Zigbee release fast -p. What is it? This is the non-mul add one. This is the dumb version, and the other one is the clever version. So -p dumb. Okay, and then we do the clever version. -p clever. Hyperfine. No, this is not dumb. Okay, there we go. They should be hopefully faster. Yeah, 2 seconds. While we wait, thoughts on commenting alternative blocks versus if through else. Commenting alternative blocks versus if through else. Oh, right. What I was doing right now versus doing if through if else. Yeah, I don't know. I don't have a strong opinion. I'm not too smart about it. Yo, am I seeing this right? Clever seems faster. Yo. Clever seems indeed no 6% faster. And it seems fairly precise. What changed? This is what makes it slower. The normal code versus a couple mul adds. The mul ads seems faster. Awesome. Very cool. Okay, where were we? 9.1, I believe, right? Oh, where's my thingy? 9.1 to do simple diffuse material. Yeah. Fast math mode. How do you do that? What's the fast math mode? Is it a flag or do I need to wire this in the build system? I've never done that. Like, I'm vaguely familiar that you can change the, like, how float works, but I don't remember. Well, I'll wait for you to tell me. In the meantime, I'm going to make some progress. Let's see. Oh, I went too far. Okay, so we implemented random stuff. Set float mode dot optimized. Okay, is this... Where do we put this? Do we put it in main? Change the current scope rules about floating operations. Strict default optimized. Current scope means that it doesn't go... It doesn't apply, right, to other functions. So we want this in wherever we're doing heavy math. So I'm guessing in getRay and in, I don't know, maybe here. Maybe here. Maybe here, not really. Okay, I'm going to rebuild Clever. Has no member named optimized. Wait, did ZLS lie to me? I'm guessing it's lowercase now. Could you believe that ZLS would lie to me? Yeah, because they're managed manually, so that's the problem. I guess they didn't get updated. Okay, let's rebuild also dumb. This does seem faster, right? This was slower for both. Now dumb is faster. Let's see if Clever gets any faster. Oh, it's the website wrong. Cool. Okay, with optimized mode, then it basically applies the transformation, it seems, and we're pretty much there. There seems to be a consistent small difference, but so it's not exactly the same. It's interesting, and dumb is faster than clever in this case, although it's really a small difference. A small difference. Well, okay, cool. I think flow mode optimized. In any case, it's good to have. I'm gonna keep it around. So what were we doing? We're reading this. Are there any visual differences? Good point. I don't think so. Yeah, I think this is just too simple. To really see the visual differences, I think we would need something way more complicated, maybe. Where you have, you know, stuff very far away, where you start seeing float error build up. That kind of stuff. Okay, then we proceed to figure out how to manipulate a random vector so that we only get results that are on the surface of a hemisphere. There are analytical methods of doing this, but they are actually surprisingly complicated to understand and quite a bit complicated to implement. Instead, we'll use what is typically the easiest algorithm, a rejection method. A rejection method works by repeatedly generating random samples until we produce a sample that meets the desired criteria. In other words, we keep rejecting bad samples until you find a good one. There are many equally valid ways of generating a random vector in an hemisphere using the rejection method, but for our purposes, we will go with the simplest, which is generate a random vector inside the unit sphere, normalize the vector to extend it to the sphere surface. So we generate another vector. We normalize it to grow. Okay. Invert the normalized vector if it falls into the wrong hemisphere. I mean, that seems actually good. Wait, are we actually rejecting anything? We're not really rejecting anything. Where's the rejection? First, we will use the rejection method to generate the random vector inside the unit sphere. Oh, because because we're using a unit square, so we could fall away. We could fall on the unit square, not the unit circle. And the problem is that the unit square is biased for these diagonals. It really doesn't like this direction or this direction, or rather, it likes these directions more, right? Because there's some extra space here that you can fall into, while here you just can't. So I guess that's why we're rejecting those guys, because if we were not going to reject them and instead we were going to just repurpose them, then we would have a clear bias. And that would introduce artifacts, which, by the way, could be cool to see what artifacts we create by not rejecting. Okay, pick a random point inside the cube and closing the unit sphere, that is x, y, z are all in the range plus minus 1. If this point lies outside the unit sphere, then we generate a new one until we find one that lies inside or on the unit sphere. Two vectors were rejected before finding a good one, pre-normalization, and then you normalize it. The accepted random vector is normalized to produce a unit vector. Cool. Here's our draft of the function, random unit vector. Vec3 random unit vector. Okay. You know what? I'm going to copy this. Copy. We're going to back. They also put in line. Ah, man. Random unit. We don't repeat vector. We're already inside the back namespace. Returns a vec3. Oh, but we're already doing the rejection in here. This is not really a random unit vector, is it? Oh, this is actually, sorry, a vec on magnitude 2, and then we pass in the vector. Then... Oh, no, never mind. This is not rejecting. This is doing the normalization. Wait a second. No, it is doing the rejection. This is saying if the length square... Right, if after squaring the magnitude we are above 1, then it means that we were outside the sphere. What if the vector is actually 0, 0, 0? We get length 0, I believe. Let me double check. Yeah, and then I don't know what happens afterwards. We'll look at it in a moment. So M2 or then 1, then return P divided by SQRT. Is this vec.sqrt? We have it, right? No, we don't. We were using the built-in. The built-in works on vectors. No, wait, it doesn't matter. This is just a scalar. Never mind. Okay. No, what am I talking about? We need to splat. Yeah, we definitely need to splat. So does this work? Oh, this is just magnitude 2 in here. What was P? My vector, right? So this seems it. So what happens if the magnitude is 0? Yeah, good question. We're going to do the square root of 0, which is not great. Do they have... I guess we can assert. Although this is random, so it can happen. And 0 is inclusive. So if... so let me think about it for a moment. If we generate a vector 0, it really has no direction. So we don't know shit about it. I guess we just reject it right away. I guess anything that isn't precisely 0 should be fine. Just change condition to use a ring. Yeah. But even if it's lower than that, right? I think the real problem is 0. Like it's strictly 0, right? Anything that isn't strictly 0, should be fine. Oh, minus 0. No, it can't because we're squaring. Magnitude 2 is the squared magnitude, so it's never going to be negative. Okay. Let's see. Suddenly we have a small floating point abstraction leak to deal with. Since floating point numbers have finite precision, a very small value can underflow to 0 when squared. So if all three coordinates are small enough that it is very near to the center of the sphere, the norm of this vector will be 0, and thus normalizing it would yield the bogus vector infinites, whatever. To fix this, we'll also reject... Oh, they also do it afterwards. It will also reject points that lie inside this black hole around the center. With double precision 64-bit floats, we can safely support values greater than 10 to the minus 160. Okay, so they don't just reject 0. They also reject something very small. We can actually do this, right? That's std dot... what was it? std dot math dot float EPS F64. I think this is it. Does it not have the E notation? What I think is more interesting is that they are making assumptions about the hardware that we have, but this is nicer because this is a function that returns the machine epsilon for floating point of type T. And this seems interesting. Epsilon is probably too small. You think so? Let's leave it like this and let's see what happens. Let's see. Now we have a random unit vector. We can determine if it is in the correct hemisphere by comparing it against the surface normal. Yes. The normal vector tells us which hemisphere we need. To do random on hemisphere. Random unit vector. And if the dot product is positive, then they're going this in direction. Otherwise, we negate. Okay. By the way, look at how everything is defined in line. Let's go. Float apps at. Yeah. Would that make any big difference in this case? I mean, yeah, it's we can do at 0, but does that make any particular difference? There you go. Random hemisphere. Okay, const v equals random unit. But we're forgetting something. We need to accept random as input because we need to pass it down. And we also need to accept a normal here. We can actually do this return. And then here we do v else minus v. Go. Okay. If a ray bounces off of a material and keeps 100% of its color, then we say that the material is white. If a ray bounces off of the material and keeps 0% of the color, then we say that the material is black. The first demonstration of our new diffuse material will set the ray color function to return 50% of the color from a bounce. We should expect to get a nice gray color. Okay, so now we're going into ray color, which is in camera. And in if hit, I'm gonna do this. Equals vec dot random me sphere. We need to pass random. I'm gonna put this here, I guess. Then we're gonna do rand and then the normal it.n. And then we return 0.5. This guy gets splatted. Times ray color. Wait, we are ray color. Wait, are we adding recursion to this thing, man? Is this a good idea? Is it really a good idea to add recursion to this stuff? Dude? Are you sure? Are you sure? I'm not sure, honestly. Yeah, the ray bounces. My point is, expressing that through recursion seems a bad idea. I would make a loop for that, not recursion. Let's see. Ray does not support array initialization syntax. Oh, sorry, Mr. Array. Have init. I guess we can do dot init. Oh, we still have the giant stuff. Okay, I'm gonna reduce these numbers after this one goes. Wikipedia article on ray tracing uses the word recursive all over the place. I think it's a pretty common design pattern for this. I guess. I guess probably it's because you don't do too many rounds. You know that you make what, 3 rounds of this? 4 rounds? I don't know. But also when you want to move this stuff to the GPU, you definitely need to move back to a loop system, right? I don't know. In any case, this looks nice. This looks really nice. Also, there's a shadow on the left. What is going on? Why do we have a shadow on the left and not on the right? What is the position of that sphere? Because I would expect then that sphere is not. You define a light source. Yes, the camera is the light source. We're basically doing both things at once, I guess. We are like looking at things, and as we look at things, we illuminate them. If you think about it, it's almost like a philosophical idea. Let me see where the word is defined in main, right? So where's the sphere? This is the giant sphere. Let's ignore it. This is right in front of us, right? This sphere being straight up in front of us, it should be uniformly distributed around. Let's see what the book does. Yeah, right. The book has it uniform. It doesn't have it only on the left. No, it's not the sky. It's our eyes. Our eyes are the light source. Why are we? Why is our light to the left? What is going on? Oh, wait. Could it have something to do with our artistic liberties that we took in defining this? Maybe. Let's use the same constant that they used. What am I doing? Shouldn't random be a random range? You're right. You know why I didn't realize that? It's because of overloading. And so I didn't realize that we were supposed to call random range. Expected statement found pub. Oh. Also, we need to stop making these giant thingies. Camera. Image width. So sample per pixel 10, image width 400. Let's go back to normality. But I will do this last render. Becoming a civil society in 1 week in new book. Okay. Is it centered now? It's centered, right? Yeah. So what we were experiencing was literally. Let me double check the code. Random range versus random. So we were creating random vectors that were outside. We were creating random vectors that were outside the square. But why were we pointing to the left then? I don't understand why failing to do the range thing got us to have more light to the left. Also, you know what I'm curious to do? Let's not really reject anything. Also, wait, let me also return our epsilon. So how do we do with our epsilon? Let's see. Ah, man, this is too small and puny. What is this thing? No, horrible. I changed my mind. I want to go back to the big image, man. You know what? 20. I'm gonna wait. I want a good image. I just can't deal with the bad image anymore. Is there built-in watch mode available? Yes, there is. It's dash dash watch. Maybe I should keep it on, but it's fine. Oh shit. You know what happened? I modified the image. Whoops. Sorry. We're doing another round without watch. I don't want watch, but it's there. I don't want it right now, but it's there. Doom. There might be 1 or 200 between 400 and 4,000. I know, but look, listen, I just got used to it. And now I can't go back. So with our epsilon, we're still good. Now, I wonder what would happen if we didn't do any rejection at all. What if we didn't do any rejection at all? Now, watch it crash hard because of NaN. Or go, no, it won't crash, right? It will just go insane. Let's see what happens. What's the reference article? It's called Raytracing in a Weekend. In 1 weekend, I believe. Or on a weekend. In any case, just search Raytracing Weekend. You will find it right away. Why is it so quick for the first 1K? Probably because it doesn't hit anything. Right now we added code that when we hit something, then we need to calculate the bounce. And so once we get to the lower half of the image, in the center because of the small sphere, and in the bottom, let's say roughly third of the image where the giant sphere is, then we need to start bouncing things. So far it seems that even without rejecting, we are not doing too bad. This still makes sense. Not using the right random function was a lot worse than what we're doing right now. In any case, it seems fine. Let's see. Blah blah blah. Here's our solution. Okay, we have that. Now we have a random unit vector. We can determine if it's no. I think we already did this. Yes. We already did this. We got this image, so we succeeded. Also, ours is much more quality. Nice. So limited the number of child rays. Max depth. Let's see. There's one potential problem lurking here. Notice that the ray color function is recursive. I did notice that. When will it stop recursing? When it fails to hit anything. Right. In some cases, however, there may be a long time, long enough to blow the stack. What do you know? To guard against that, let's limit the maximum. No! You turn it into a loop, right? And then you maybe also have a limit to the loop, but you to guard against that, let's limit the maximum recursion depth, returning no light contribution at the maximum depth. I'm not gonna do a transformation to a loop because I fear that if I do that, then I'm gonna I'm gonna diverge too much from what they want me to do. So I just don't want to go insane. So let's go with the max recursion limit. We pass max depth to ray color and ray color. Yep. Okay. If level equals 0, they do it by subtracting. I think I would actually go up, honestly. Was it max recursion? I think it's so I think that if your numbers are implemented as a JavaScript array, then I think that going down is more efficient. Yes. Okay. Next. Oh, and then we do 50. For this very simple sim, we should get basically the same result. Okay, so I'm not gonna do that. Fixing shadow acne. There's also a subtle bug that we need to address. A ray will attempt to accurately calculate the intersection point where it intersects with a surface. Unfortunately for us, this calculation is susceptible to floating point rounding errors, which can cause the intersection point to be ever so slightly off. Okay. This means that the origin of the next ray, the ray that is randomly scattered off of the surface, is likely to be perfectly flush. Is unlikely to be perfectly flush with the surface. It might be just above the surface. It might be just below the surface. If the ray origins is just below the surface, then it would intersect with the surface again, which means that it will find the nearest surface at t super small, and whatever floating point approximation we hit, and whatever floating approximation the heat function gives us. The simplest hack to address this is just to ignore hits that are very close to the calculated intersection point. That is a good point. Wait, why do we have a skewed shadow? Do we? Do we have a skewed shadow? No, we did at some point, but we don't anymore. I fixed it. We were calling the wrong random function. Now it's fine, I think. This looks fine to me. I'm looking also at another monitor. Like I have a monitor with like the programming monitor they have has a ton of burn in. So it's actually hard to evaluate ray tracing because there's way too much from the screen already. But yeah. So yeah, no, we were calling random instead of calling random in a range because they didn't recognize that there was like an overload. Let's get rid of the acne let's get rid of the acne problem. Yes, it's really called that. Here's the result. Is there any difference? I'm actually kind of curious to see this. So let's see. World heat interval. So instead of 0, we give something small. Okay. This didn't hit everything, right? Mean is 0.1. I think it might have improved slightly, but I'm actually not sure. This might be entirely placebo effect. I don't know. What do you guys think? It's a lot better, yes. Okay. Could we put here something that is smarter than 0.1? Could we put here some like kind of nice epsilon? Whatever. It's fine. Generate two images and compare. Yeah, no, the problem is that I have a shitty monitor, so it's really hard for me. And then I have the OBS preview, which I guess it's better than nothing, but it's also scaled down. So you guys have to help me here. I just can't on my own. I also have my eyes there. I should buy better ones as well. Through Lambertian reflection, scattering reflected rays evenly about the hemisphere produces a nice soft diffuse model. But we can definitely do better. Also, we are finally back to the point of how do you do materials in a more realistic way. A more accurate representation of real diffuse objects is the Lambertian distribution, which is not normal. What? What is this distribution? Well, I'm not going to Google. I'm going to read more. This distribution scatters reflected rays in a manner that is proportional to the cosine of a Greek symbol, where the Greek symbol is the angle between the reflected ray and the surface normal. Yes. Of course. This is what I was talking about earlier, right? When a ray hits this way, then you look at the normal and you want to mirror the vector after that. Yeah, that makes total sense. I was actually right, although I'm not sure how that is a Lambertian distribution. Like, what does the distribution look like? But in any case, this means that a reflected ray is most likely to scatter in a direction near the surface normal and less likely to scatter in directions away from the normal. This non-uniform Lambertian distribution does a better job at modeling material reflection in the real world than our previous uniform scattering. That's phi. Thank you. Wait, usually pronounced like fine? Oh, phi. I see, so you pronounce it phi. I think in Italian it would be phi. Cool. We can create this distribution by adding a random unit vector to the normal vector at the point of intersection on a surface where there is a hit point P and there is a normal to the surface N. At the point of intersection, the surface has exactly two sides. Yes. So there can only be two unique unit spheres tangent to any intersection point. Oh, wait, no, this is saying something different than I thought. Now, my assumption was that R would go here and thus bounce the other way, but it does not. So what this is saying is that the bouncing is biased towards the normal, but not in a reflective manner. I guess that is a property of more reflective materials, maybe, like what I just described. So I'm guessing matte stuff behaves more like this, but it doesn't follow the... But it doesn't, mirror it to the other side. In any case, so one sphere will be placed in the direction of the surface normal N, and one sphere will be placed in the opposite direction, minus N. Okay. This leaves us with two spheres of unit size that will only be just touching the surface at the intersection point. From this, one of the spheres will have its center at P plus N and the other one at P minus N. The sphere with the center at P minus N is considered inside the surface, where the P plus N is considered outside the surface. Okay. Yes. We want to select the tangent unit sphere that is on the same side of the surface as the ray origin. Pick a random point S on this unit radius sphere and send a ray from the hit point P to the random point S. And and so the distribution here is based on the fact that, to go down here, you basically have to pick a point down here, while any point up here, there's more like diameter up here. than down here, I guess. And so that's why it's biased toward being near the center. I get it. And so that produces some kind of distribution, which, I mean, it probably still looks like a normal, I think, ish. Maybe, I mean, probably not a normal because otherwise it would be called a normal distribution, I guess, but close-ish, maybe? Okay, okay, this is the math. I get the idea. I don't think I would be able to get the vector math right first try on my own. If I have to be honest, I would have to stop down and think about stuff, which is hard to do while streaming. It's also hard to do while not streaming, but I'm also streaming, so that's my excuse. Hey, Christoph IT, I wanted to ask, how is the new breaking change of Zig affect the code bases of some projects? Oh yeah, of course. It affects a ton of projects, and you have to do a lot of work to get everything up to speed. And this doesn't sound sexy, and in good part it's not. But here's the thing: the new API is much, much better, and it allows you to rethink how you're doing readers and writers in your program. And if your program is heavy on input-output, and you take the time to reason about the new API and how that can impact performance, you can actually get significantly better performance. Well, no, significantly might be too much, but you can get a detectable amount of performance improvement by upgrading. So, yeah. Okay, so we get a hit. And then we take the normal. We add a random unit vector to the normal. And that is the direction. Wait, is this it? This is all the math that ends up happening? I expected something more intense. So we get the normal from the heat, yes. And we add a random unit vector to it. Yes. Okay. So we have to go into sphere heat. Wait, what am I doing? No, it's not here. It's in camera ray color. So instead of random hemisphere, we take the normal. So random hemisphere, we don't use it anymore at all. And now it's just the normal plus a random unit. Now, though, wait a second. This makes us call ray color with this ray. And then we give this ray to... Well, sorry, we are ray color, sure. We give it to hit everything. Hit everything, passes it to object hit. And here we have array. Okay. And we call everything. Okay, let's see what happens. We got a compile error. Expected one argument. Oh yeah, we need to pass random to random unit. We have random in the camera, right? So we should be able to do rand. Yeah. Okay. Also, you know what? Wait, here's what we want also. In build.zig, in zig build run, guess what we want to do? So when you call run, we execute the program, and then run command, get install step, add run artifact. This runs the command. So here's also what we want to do. We want to also to do this const open equals b dot add system something. add write file, update, remove, fail, fnt, translate, user, install, object copy, install file. There we go, add system command. Add system command, and we want to give it open emg, what is it, emg.ppm. Let's see if we can do this. And then we do open, you need to redirect the output to emg.ppm. Yeah, I mean, so far I have them doing it in the location, so that should actually work even as is. I could code it in here, obviously. Yeah, I could also put and open, couldn't I? Could I? You know what? Yeah, let's not do this. Okay, I'm sold. Okay, is the image significantly different than before? I'm actually not sure. I can't tell, man. My eyes are bad now. Let me I guess open 2 instances of it and see what happens. Oh no. Okay, I'm gonna move it. The images are similar. Oh god damn it. Okay, then whatever. It's hard to tell the difference between these two different diffuse methods, given that the scene of 2 spheres is so simple, but you should be able to notice 2 important visual differences. The shadows are more pronounced after the change. Both spheres are tinted blue from the sky after the change. Okay. Both of these changes are due to the less uniform scattering of the light rays. Sorry, there are light rays. More rays are scattering toward the normal. This means that for diffuse objects, they will appear darker because less light bounces towards the camera. For the shadows, more light bounces straight up, so the area underneath the sphere is darker. Not a lot of common everyday objects are perfectly diffuse, so our visual intuition of how those objects behave under light can be poorly formed. As scenes become more complicated over the course of the book, you are encouraged to switch between the different diffuse renders presented here. Most scenes of interest will contain a large amount of diffuse material, so you can gain valuable insight by understanding the effect of different diffuse methods on the lighting of a scene. Okay. CPU. Using gamma correction for accurate color intensity. Note the shadowing under the sphere. The picture is very dark, but our spheres only absorb half the energy of each bounce, so they are 50% reflectors. The sphere should look pretty bright in real life, a light gray, but they appear to be rather dark. We can see this more clearly if we walk through the full brightness gamut for our diffuse material. We start by setting the reflectance of ray color function from 0.5 to 0.1. Okay. I heard that Zig can compile to Spear V and wanted to know how Zig is as a shading language. Oh Jesus, it's a very dark scene. We're not reflecting much, huh? And what about 0.9? I don't remember. I don't know if the book wants you to do 0.9 or not, but I'm doing 0.9. How is Zig as a shading language? I cannot comment on that myself. Okay. I cannot comment on that. Also, okay, I can see that the shadow is kind of pointed, dotted, grainy. How do we make it less grainy? Is it more samples per pixel or is it more bounces? Also, you know what? I'm gonna move Mark's recursion up here because it's another one of those that we change. What if we recurse 20 times and we did 50 samples per pixel? So yeah, I cannot answer how good Zig is a shading language, but and that is partially because I haven't done it myself, but also partially because I believe that the SphereV backend is not fully complete. I think it can be used to do some stuff, but I believe that the last time I checked, it was mainly a matter of supporting compute shaders, not graphical stuff. I don't know if that has improved over time. Probably has. I haven't checked in a while. Maybe let's parallelize this. I'm gonna wait. I'm not gonna do big transformations until the book wants me to do those. I don't want to get stuck. It doesn't seem that we have gained much though. Even though I bumped up the numbers, nothing much has changed. So fine. Let's leave it like this. Okay. So what are we doing then? So 0. Blah blah blah. Okay. So we did the extremes and you get this. Sounds good. If you look closely, or if you use a color picker, you should notice. By the way, I'm also colorblind, so I don't know what I'm doing right now. You should notice that 50% reflectance render, the one in the middle, is far too dark to be halfway between white and black. Yeah, but I'm guessing it's because our perception of light intensity is non-linear. I'm guessing. Indeed, the 70% reflector is closer to mid-grade. The reason for this is that almost all computer programs assume that the image is gamma corrected before being written to an image file. This means that the 0 to 1 values have some transform applied before being stored as a byte. Okay. Well, let's continue. Images with data that are written without being transformed are said to be in linear space, whereas images that are transformed are said to be in gamma space. It's very likely that the image viewer that you're using is expecting an image in gamma space, but we're giving it an image in linear space. This is the reason why our image appears inaccurately dark. Okay, let's do linear to gamma then. Oh, it's square root. Okay, so this is the curve. Let's see, there are many good reasons for why images should be stored in gamma space, but for our purposes, we just need to be aware of it. We are going to transform our data. I'm not an expert with this stuff, but I think we can make an educated guess, right? Usually when you want to move away from linearity is because a given range is more important than the extremes. And the precise curve depends on the type of instrument that you want to give that value to. In our case, the instrument is our eyes, but the same is true also for our ears. So it does make sense that you do not want to spend equal bytes on every section of the range of possible values. I think a very interesting example of this, which I'm not sure if it's exactly the same point as gamma, but it's, for example, actually, you know what? No, never mind. I don't think it is. But point is that I think we do the same also with audio, at least to some degree. So let's implement linear to gamma. So this goes inside back, I believe, and it's near color format. To gamma, and I guess actually, is it a color? I guess we're doing this to everything, right? Yeah, we're doing it to R and G and B. But it's still F64. And we can actually return it into an integer from no, let's not do this here. So yeah, to be fair, I think we can do better than this, can we not? It seems to me that we can do this on the vector. Although we need the int from float at the end on every single thing. You can't call int from float on a vector, right? Oh well. Oh, if linear component, whoops, I think we did something bad. This is if linear component is greater than 0, we square root it, otherwise it's 0. You can. So let's see, you call clamp, and then you lerp. Okay. I think I'll leave it as is for now. But we got a problem earlier. So let's see what's happening now. Oh yeah, it's very dark. Oh my god, it's turbo dark. Where did we leave our reflectance at? 0.9. This was supposed to be 0.5, right? That was the original version. But I think shouldn't the gamma be done on the row float instead of the multiplied one? Yeah, I think you're right. Hello? Okay. Yeah, I think you're right. There we go. Yeah, this looks lighter. Okay. Yeah, we got the middle one, I think. Metal. Oh, let's go. No. I read metal. I was excited. I read an abstract class for materials. God damn it. If we want different objects to have different materials, we have a design decision. Yes, we have a design decision, but you do not have to solve it with fucking inheritance or abstract classes. God damn it. We could have a universal material type with lots of parameters, so any individual material type could just ignore the parameters that don't affect it. This is not a bad approach. Or we could have an abstract material class that encapsulates unique behavior. I am a fan of the later approach. Well, I'm not. For our program, the material needs to do two things. Produce a scatter ray, or say it absorbs the incident ray. And if scattered, say how much the ray should be attenuated. Right. You know what? I'm actually curious to take a moment, to take a break for a moment from what the book wants me to do. Here's what I'm thinking. I would like to try the reflection that I had in my mind earlier, which is the one where we reflect past the normal. But I don't know what is the math to do that. So right now we're doing this, right? So right now we're doing this. We're doing this is the sphere. This is the normal. This is no, this is just a bad drawing. This is the ray that hits here, and we're reflecting it towards here. How do we reflect it towards there? This is what I would like. I would like for these two angles to be the same, right? So here we have another one. This is the normal. The outgoing one should be like this. Same angle here, same angle here. Well, same angle here, same angle here. How do you do this? I forgot too much about vector math to know how to do this right away, but I would like to do this. If Anybody knows in chat how to do this? I would be interested in a suggestion. Otherwise, check section 10.4. Oh, so we're pretty close to it then. Here, geometry reflected. I would like kind of a spoiler, but not by spoiling myself the book. Okay, so we have this. So we need to... Okay, ours points this direction. So to get this, we would need to... Yeah, we need to negate it. And then... RR... Let me zoom in a little bit. RR is normal... Uh-oh. What are these operations, though? Is this just normal vector multiplication, right? Wait, what even is normal vector multiplication? Is this per component multiplication? Or is this something different? R1 dot n plus A. Oh, god damn it. Let's see. The result is determined by straightforward geometry as follows, where dot indicates the dot product, and typically n and R1 are unit vectors. We have, I think n is a unit vector in our case as well. R1, is R1 a unit vector? I'm not sure. In any case, so it's R1, so it's our ray negated dot product with the normal plus A. Oh, we don't have A though. Fuck is A? A is the distance. Yeah, the fuck is A? Oh, I guess A goes away with reasoning. Awesome. So RR is our... Oh, our initial ray minus 2 times n multiplied by Ri with dot product with n. Okay. Let's YOLO it and let's see what happens. And then we can have the book tell us how to do it properly. So, yes, we do want to calculate a better direction. So let's see how we do this. We have the original ray, and we're saying this thing says where did it go? Oops. I'm gonna move this here. Sorry, chat. Actually, no, we can keep chat around. No, oh, you know what? There we go. I found the trick. Almost, I think. Yeah, that one is the formula that we want. Okay, so direction is the original ray minus 2 times. I think this is plotted too. No, I'm actually wrong. Wait a second. Because we're calculating, we're doing a dot product. So this is not a plotted too, right? So dot product, this is vec dot dot of ray dot direction. Yeah. And normal hit dot normal hit dot normal. Then this is times 2. And I guess this is what needs to be splatted. This splat that I'm doing seems super suspicious. Oh no, wait, there's an N outside. Oh, there we go. Yeah, that's what made it suspicious. Yeah, so it's 2 times N times like the splat. Oops, this is times, not an N. And N is hit.N. I have no idea if this math is right or not. but let's see what happens. Let's see vector here. What happens? Mix the scalar and vector operands ray and vector 3. Oh yeah, because this is r dot direction. Now watch my completely borked math. Yo, it's not borked at all. Let's fucking go. We did it. The problem is that we made everything perfect. There is no noise at all, so it has these weird bending problems, I guess. Let's add some noise. Just a tiny bit amount. I mean, what if I just added a random unit? Right? Just a little bit, just a random unit in there. Oh, we're back to this shit. Never mind. We're back to this shit. We didn't gain anything. Random unit is too much. Right. What is the problem? The problem is that, yeah, we're scattering it still a lot. What I would want is to scatter it just a tiny bit amount. It's like just a tiny bit amount of noise to make it just not slightly not perfectly reflective, right? That is the problem. So how do we do this? I guess we want to scale this. Let me think about it for a moment. We just want to scale this because random unit is too much. I think we want to divide this by, or multiply this by like 0.01. Which I guess I could do also with random range. I don't know. Let's do it like this. Let's see what happens. What's the problem? Is scalar vector, operands vector, and struct. Oh god damn it, man. Yeah, I think we got it, right? Let me make it let me see if we can make this let's increase the effect tenfold. So my expectation is that it's mostly reflective, but slightly borked. Well, not borked, but like not perfectly so. Yeah. I mean, it's probably, it's not the greatest effect visually. There's probably some more sophistication if you want to make something compelling that is required. But I can see it a little bit. That is cool. Okay, success. By the way, thank you very much. Thank you. Who shared this link? JW01, thank you very much. That was awesome. That was precisely what I wanted. You gave me the formula, but it wasn't by spoiling the book. Thank you. Oh, also, wait, let's revert the weird changes that we made. So I want to take this out. Let's keep it pure. And this is the one that we have right now engaged. Okay, there's a structure to describe ray object intersections. Oh no, wait, the material. Wait, materials are not hittable. They have scatter. So the material decides. Right, so the scattering is implemented like this. That's fair. So we have material, and then we have that a hit record has a share pointer to the material. A hit record has a reference to the material. The reason for this is because the hit doesn't compute any of the like bouncing ray. So we need to remember what material we hit inside of it. Yeah. That makes sense, I guess. But it seems weird though, right? Because on the other hand, what you would want is the sphere instance to have the material, which I'm guessing you will have to do anyway. So I guess you basically start with that, and then you give the material also to the hit. You pass it. Basically, you attach it to the hit. And the reason also why we're doing this is because we only have the hit in here, right? We don't have any information about what got hit. Okay, so we need to create materials. I think I'm going to create material under objects. We already created hit and interval in here. Again, I'm not sure if this is the best place where to put this. You could argue that inside objects there should only be objects, which would be fair. But I don't know, we're placing this stuff in here, might as well. Pop const material equals struct. And the material has a function. So we are... The material has a function. They're doing all this fucking inheritance for no reason. Why is it like this? What if instead we said that the material is an enum, huh? And we have, I don't know, velvet, metal. And then we have pub function scatter and takes in the material as an enum. No share pointers, no weird shit. And this returns, I guess, a vec3 for the new direction. And it probably takes in the hit. And it takes in... What else should it take in? I think the hit has everything. I don't know. Well, let's start with this. Okay, let's start with this. Then we said that a hit needs to have a material. Yeah, I know. I'm just leaving there as placeholders. So the hit has a material. The sphere also has a material. Then a hit returns a hit, and we give it also our material. Then in the camera, by the way, I'm doing this trying to reason instead of copying from the book. Why would you put material in sphere? Can't you just pass material as parameter in hit function? Well, because the idea is that we want to be able to create spheres made of different materials. So the idea is that the sphere remembers when you create it which material it's made of. So like we go in main basically, and we say sphere, and this one is gonna be, dot dot velvet, and this one is gonna be dot metal. And so in what am I missing next? Here, right here, we're making the decision on what the direction should be. We're also making a decision about the reflectance, right? Probably that also should become something that the material does. But I guess we'll... By the way, I'm pre-signing this for now, but I'm gonna go back to the book in a moment. So here we do, const direction equals heat dot scatter, I guess, and we give it the ray. I haven't implemented heat dot scatter, so I'm going to hit. So I'll go back to object. Let's give scatter to hit. Also, we're gonna need rand. This is a choice that we made, and that everything that needs random we pass it down. So yeah, but so do we not read R? Yeah, we do need R, for example, down here in this case. But it turns out that we don't really need the material. Oh, right, because we need to decide. So switch material. So for example, this would go here. And I guess we can do like this, return. There we go. And then, I don't know, we do one of these guys. Let's see, repeating since you might have missed it, but you might want to make material a tagged union to be able to define parameters on your materials. A tagged union. I see. I mean, let's see. So far this seems fine. Let's see if we compile or if I mess something up. Need 3 arguments, right? I need to pass around random. So this scatter needs to accept also random. Oh, random hit. That makes sense. Which is H in our context here. Okay. Let's see how closer we are. In camera, right. Okay, it seems so far so good. That works. Now the bottom sphere is perfectly reflective. The upper sphere is velvet. Let's do the inverse. Delightful. we got it. Okay, let's see what the book wanted us to do. So a class hit record has a shared pointer to a material. Then the sphere takes in a shared pointer to the material. Modeling light scatter and reflectance. Let's see, the material here has a color. Oh, we want to give a color to the material. Okay. You know what? Give me a sec because I need a quick bathroom break. And I'm going to be right back. And then we can do this part. So yeah, we don't have properties given to these materials, right? I guess the question is, are materials like there's like different kinds? I guess you can have different kinds of velvet, right? And so the idea is you parameterize the velvet. We can do that. So that would mean, yeah, making a tagged union, and then we say velvet is parameterized by color and this other stuff. That makes sense. Okay, so the suggestion to make it a tagged union is good. I'm gonna do that next. I'll be right back. Okay, I'm back. Let's see. Okay, so we're saying, oh yeah, right. We want to make these materials a little bit more interesting. Okay, so let's go from an enum. Let's go from an enum to a union. Enum and union. Okay, so Velvet. What does Velvet have? Color and I don't know. Also, what's color? Vec3, I guess. RGB. Then metal. What does metal have? Metal doesn't have a color, right? It just has a like how much it diffuses. I don't know, diffusion. There's probably better names. Anyway, I'm just gonna do these and really stop ad-libbing. Color is albedo. It can have color. I mean, I guess. Okay, sure. Let's give it color. Yeah, I guess you can have like a metal that has one that is bluish, one that is darker gray. Oh, that makes sense. Okay, so let's see. Random unit. Right, but we can't use these at all right now because we're returning a direction. So what do we do with it? I think for now we do nothing. Let's leave it as that for now. You know what? Let's go back to the book because the book will want us, I think, to do something different. Oh, no. That makes sense. We don't use it here. We use it in camera. Here we take the direction. And then... where do you use these colors? This is it, right? This is like some color vector that we should not code. You know what? It's time to go back to the book. Let's go. Okay, a material has. Let's see. Here in front of these books, we will use the term albedo, Latin for whiteness. Albedo is a precise technical term in some disciplines, but in all cases, it is used to define the form of some form of fractional reflectance. Oh, so when you said albedo, wait, color is albedo. It's not the color. It's the how reflective the thing is. Albedo will vary with material color, and as we will later implement for glass materials, it can also vary with incident viewing direction. The direction of the coming ray. Whoa. Lambertian diffuse reflectance can either always scatter and attenuate light according to its reflectance R, or it can sometimes scatter with probability 1 minus R with no attenuation, where a ray that isn't scattered is just absorbed into the material. It could also be a mixture of both of these strategies. We will choose to always scatter, so implementing Lambertian materials becomes a simple task. Okay. He's creating a fucking class for this. So what is a Lambertian material then? That's what I call velvet then? I guess Lambertian is velvet in my case. So Lambertian, then color albedo. So you were right. Color is albedo. Okay. But wait, the description above doesn't say that color is... I'm confused. Okay. In any case, blah, 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 blah. So this is the scatter implementation. So normal plus unique vector. And then also this modifies the ray and returns a boolean, and it always returns true. Oh, because now sometimes we don't return anything. We absorb sometimes. Okay, so this returns an optional vec3. This returns an optional vec3. For Lambertian, then what we were doing, we do normal plus random unit, and then we create an array that has the direction. Oh, so we don't return the entire, sorry, only the direction. Return the new ray that starts from the position P. And then we return also the color. We're returning 2 parameters. Okay, let's do a proper job then. So let's do a proper job. We return, let's say that we return a scatter. So const scatter equals struct. And this contains a new ray and a color. Although they call it attenuation. Is this something that we multiply? How does it work? How do we make it work? Do we what? We multiply it. I'm assuming that this is this guy. But I'm not sure. Let's call it attenuation. Okay. Okay, so we get the direction, and then we make it a scatter. Then is dot ray equals dot origin equals hit dot p dot direction equals direction, and then dot attenuation equals material dot Lambertian dot albedo. Let's go with the full name. Okay. Then metal. Well, I guess we made our own formula for metal, so I guess we keep that around. So we return. Okay, we have to decide what to do with the attenuation in this case. Let's put a comment in here. How does that work? Disgusting. Let's put a comment in here. That did not solve much, did it? That did not solve much, did it? Guess we can do this. I'll take this. Okay. So we return a scatter, and this returns a scatter, optional scatter, optional material dot scatter. We'll make this public so that others can also access it. And then we go in camera, and so we scatter. We don't get a direction, but we get more than just the direction, right? We get a, if it's present, so scatter is this, or else return back.0, I guess. And then what do we do with the scatter? So the scatter is an attenuation and a ray. So this is the ray. And what do we do with the attenuation? Is this? No, because it's a color. So okay, let's see what they want us to do. Let's see. Note the third option. We could scatter with some with some fixed probability P and have the attenuation be albedo over P, your choice. I don't know. I'm fine with what we already have. If you read the code above carefully, you will notice a small chance of mischief. Ooh, mischief? What happens? If the random unit vector we generated is exactly opposite to the normal vector, the two will sum to 0, which will result in a 0 scatter direction vector. This leads to bad scenarios later on, infinities and nans, so we need to intercept the condition before we pass it on. Not a bad approach. Although, are you sure? Maybe we could scatter everywhere a bunch of checks against infinites and nans and then turn those bogus numbers into 0 or 1 or 5. That also works, apparently. Anyway, in surface of this, we'll create a new vector method called near 0 that returns true if the vector is very close to 0 in all dimensions. Okay. Oh, fabs. The following changes will use the C++ standard library function SED fabs, which returns the absolute value of its input. Okay. So this is our epsilon. And this is how we do it. Wait, is there a better way to do this? You did it a few times already. I did it with the magnitude, but I'm not sure with the magnitude squared, but I'm not sure if that is the best way of going at it with the entire, like compared to checking the 3 arguments individually. In any case, const this and then const x equals, oh, I can't, underscore x equals you have ABS. You don't have ABS? Approx equal ABS. Yeah, that's what we want, right? Does it take vectors? No, it only takes floats. Yo! Okay, let's see. How does this work? Return at reduce and ABS of, instead of E, that would be the vector, right? I wish in our case it's just splat. Cool. Okay, we still have some things to figure out though, I think. So let's continue with the book. Then in Lambertian, catch the generate scatter direction. And if we get it, then scatter direction is the normal. Okay. Or we could not scatter when that happens. But fine. Man, they do it with, god damn it. They also they also do it with mutating. They mutate state. That is so annoying. Why do they like this approach? I don't get it. There you go, without mutating anything. Okay, so this is done. What's the next point? Wait, there's stuff that you didn't show though, because it's showing that scatter now has a attenuation signature. We're still far from usage. I guess we went, oh, there we go. Mirrored light reflection. For polished materials, the ray won't be randomly scattered. The key question is, how does a ray get reflected on a metal mirror? And the vector math is our friend here. Oh, there's how you do it. You take the vector, you move it from starting here, and then I guess you flip something. In any case, well, okay, so here's the math, which we already did. Reflect. Oh, they added reflect to vec 3. Honestly, that's not a bad operation to have on a vector, huh? That returns scalar. Right. So in our metal, yeah, that's what we did here. The end just moved to the right, basically. Just put it in one splat. Good point. Okay, that's cool. Oh, there we go, metal. So we reflect. We make a ray. Attenuation is still equal to albedo. So metal also has albedo, apparently. Okay. We need to modify the ray color function for all our changes. Yeah, so what do we do with this stuff? Okay, yeah, so attenuation is not a splattered number anymore. Oh. Okay, so it wasn't the weirdo vector that the weirdo vector I guess is something else. Is this the sky or something? in any case, camera. Then we get the scatter and yeah. And so this is there we go. Attenuation. Okay. It should actually get us in working condition. So let's fix programming errors that we have. Recursion from enum. Okay, so in world, in main, we need to do something better than this. So metal is going to be a material. So const material equals objects material. So this material is going to be dot Lambertian. No, metal is metal. And has albedo, which we don't know what it is. Undefined, I guess. I'm going to say velvet. Conversion. And I don't know, maybe we make it red. Okay, what's next? Accessor type vector found bool. Right. That's me. Next. No field name normal in start object.hit. Yeah. Objects 59. Actually, maybe this fits one line. I should not have done that. That's not how you do it. It's this how you do it. It's not great. Okay. Yeah. Big red sphere makes the other sphere red. What if the other sphere had its own... wait, what did I do in main? For this guy. Oh, it's completely undefined. That's not good. So undefined is not good. Also in objects, how do we do the scatter in the case of metal? Yeah, we just pass it down. So okay, we have some undefined stuff that should be there. I don't know what this should be. Just pure white. That makes sense. That makes sense. I get it. This makes sense. And so we can make it blue. That's a lot of blue. Yeah. And okay, it's like this is very dark. So what if we do 0.2? Yeah, okay. What if we make this a 1 and these guys are like 0.6 and 0.6? So this should be a blue sphere, but lighter. That's what it is. Not bad. Man, it also computes this curvature here. This is delightful. This is truly delightful. Okay, what's the next thing to do? We'll update sphere constructor to initialize the material pointer. Yes, I've done this. Oh shit. What? More spheres? I forgot that you could do this. Yeah, more spheres. And then what materials do they have? 2 Lambertian materials, 2 spheres. Okay, let's copy this and let's see how we do this. Also, max depth is set to 50. And samples per pixel is 100. Okay. Okay. So we have, let's see, spheres. Instead of 2 spheres, we have 4 spheres. This one is this one. And it has material ground, which is a Lambertian 880. Okay, let's go. Let's do the same thing that the book wants to do. Ground 08080. So that's ground. Maybe we can take out a couple commas. Oh right, there's too much C coding here. Yeah, this is all CPU. How are you handling the polymorphism? Yeah, I'm not doing any virtual function at all. Like the material is a tagged union. And the tagged union has one scatter implementation with, all the code. And if you want to be a little bit cleverer, like if you don't want to put this in one big switch, then you can give each case its own implementation of scatter. And then you can use the union wide scatter implementation to just dispatch to the scatter implementation of each case. So that might be, nice from a perspective of code organization, because then you can even define metal in its own file, Lambertian in its own file. So that works. Yeah, it's static dispatch. Well, it's not entirely static because we're switching at runtime over the tag, but it's definitely not virtual functions. So there's runtime branching, but no pointer chasing. Okay, so material ground. So we want the sphere that is this one goes up above. We'll give it ground. Okay, done. Then we have 0, 0, minus 1.2, 0.5, and it's center. What's material center? It's another Lambertian. Okay. This one has 0, 1, 0, 2, 0, 5. Okay, this is done. Then we have minus 1, 0, minus 1, 0, 5. This is called left. And it's a metal material. And it has albedo 080808. Okay, and then we have right, which is another metal material. This one has 080602. Okay, so this guy gave left. I think this guy is fine. This guy is 1, 0, minus 1, 0.5, right. Okay, take this out, save. Single line, I don't know, like this maybe. This looks good, honestly. I'm gonna do this. That seems not too bad. Okay. Let's see how it goes. Oh, wait. So still a small image. We have a much bigger image, much bigger resolution. I'm not changing that. I want to keep that. They do 100 samples per pixel and 50 depth. Let's fucking go. Camera. 100 samples per pixels and 50 depth. Let's go. So my recommendation happens is I understand. Obviously, I'm also trying to do the same. But the virtual function pointer chasing stuff is absolutely unnecessary. Like absolutely. The reality is that might become interesting if you have like a plugin system where somebody defines in a DLL their own material with their own scattering implementation. And even then, what I would do is still have the built-in materials, not use that technique. You still switch on the on a tagged union, and then you have a case for like an external material, and that's the one that does the virtual dispatch. And because you pay the price for performance if you don't do that. Man, I can't wait. Give me the result. Man, it is slowing down, huh? We're right now. I think we are feeling hard the 50 levels recursion. I could probably add some extra information in our progress bar. Time to spin some threads, huh? Try pull time. So how does it work? You do, I guess, you do multiple pixels at a time, right? Or batches, right? So the idea is, I guess you're right. You can just divide the space into like squares, and each thread does its own square. One job for each line. Yeah, I guess it depends on how you want to divide the load, because you can do, for example, one job for each line, but lines up above where there's no collisions are going to be super fast, and then lines down at the bottom are going to be super slow. That said, you have enough lines to give to threads, so that shouldn't be a problem. Just divide pixels per threads. I think that having a pixel level of granularity for your jobs is you pay too much synchronization cost, I suspect. You do want some batching. Or if you mean like you divide the image like in blocks. Yeah, of course. But then at that point you can do it per line. Per line is fairly natural given how we're looping, and you don't have to think about it much, I guess. Yeah, okay, I'm gonna run this one to completion, and then maybe we can start thinking about that. Does the book do that? Let's take a look while we wait. Let's take a look at what the book wants us to do. Fuzzy reflection. We can also randomize the reflected direction by using a small sphere and choosing a new endpoint for the ray. What? We'll use a random point from the surface of a sphere centered on the original endpoints scaled by the fuzz factor. I'm not sure I understand what this is doing. So for metal... Wait, this is doing what I was doing. This is adding a random unit vector, scaling it for a fuzz factor. Would you look at that? Look at this delightful defensive programming here. Yo! There we go. You can even see a little bit of... the other sphere behind. This is so cool. Is it supposed to look like this? Wait, it's actually not supposed to look like this. Yeah, I fucked something up. Right, it's not that guy. It's this guy. Why is the bottom like that? So if we want to diagnose this, we have to make this multi-threaded, or we reduce the quality. I guess we can reduce the quality. What if this were 400? Out of curiosity, how long does it take then at that point? Oh, it's very fast. Yeah, but it's borked. We borked the math at the bottom math. Have you checked your reflectance formula with the book, or did you keep your own? So, because the problem is metals, right? Let's take a look. So, oh. Actually, you know what? I'm not sure we're doing this correctly. Let me double check. Yeah, I need to double check a few things, I guess. So let's go into ray color. Yeah, okay, we do this, or else return back 0. So this we do correctly, I believe. So I think this is fine. It's the metal stuff, right? That is probably the one that has issues. So let's take a look at metal. You know what? I think I want also to break these things up. Let's break them up. Let's do this. Check this out for those who have never used it. What do we call these? There we go. Not bad, huh? So now our this patch is just done with adding line else. And here we call all the dedicated functions. And right now metal doesn't even care about randomness. But maybe we're messing something up. Let's see, what do we do here? Reflected. So we reflect the ray, the direction of the ray against the normal. So this is correct. unless the formula is borked, but this should be correct. And then we just pass down everything as it as we were doing before. I don't know. Either I'm doing the reflect wrong, or I really would not know what's going on. Normal is not unit. Because you think that one of these guys, because you think that this would not be normalized. Let's see what Lambertian was supposed to be. They have these. The scatter direction is this. There's no normalization happening here in the code. With the writer gate PR from Andrew Kelly break projects you did so far, it already has, and I've already updated them. How did you do the vector math? I thought Zig doesn't have operator overloading. It does not. But there's a vector type, and it does vector operations between vectors. So I don't know what we're doing wrong. Maybe I'm getting the origin wrong. Maybe origin isn't just hit.p, but I think it is. Rec.p. Oh, also in Lambertian. Do we do it also in Lambertian? Direction is, yeah, hit.p. Okay, so we do this correctly, I think. What if we do this? This is wrong, but... Wait a second. We're not using Ray in Lambertian? We're not using Ray in Lambertian? Really? Ray in is not used anywhere. That is correct. It is weird, but correct. We made it worse. We definitely made it worse. Okay, so could this be wrong? But no, it shouldn't. Like, if we're making absolute values of the vector, and then we're reducing. Sorry, let's look at the original implementation. Yeah, no. Also, the original implementation was doing the same. No, this seems fairly clear cut that this should be correct. That said, I think it seems like this is where stuff is going weird. Let me just double check one thing also, that that in main we initialized everything correctly and we didn't do anything weird. So ground, center, left, right. And ground and center are Lambertians, and then the other ones are metal. Let's see. Ground and center are inversion. The other two are metal. One has 100 size and it's very down below. The other ones are smallish. Yeah. Okay, so these bring us back to the problem, which I think we're experiencing both here and here, right? And it has to do with reflections that they are very close to the points near the norm. Since n plus unit has length 2, out of curiosity, what if we made this more restrictive? We still have the same problem. Okay. What if we did this the opposite? Okay. Reduce number of recursions. Could fast math cause this? Oh, good question. I don't know. No, that's not it. Fast math is fine. What could we be messing up? Try to reduce the number of recursions. We could do that, but the recursion makes stuff lighter, right? It doesn't make stuff darker. So the fact that this stuff is darker is not the recursions. The recursions only add color; they don't subtract. What's happening is that in situations where reflections are happening very near the normal, something goes out of whack. Out of curiosity, what if we didn't do this? Transitioning from 0, 1 to 0. Oh, shit. You know that. You know what? Yeah, you're right. This is it. This is probably what's happening. That is a good point. That is a very good point. Yeah. 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 I think we got it. Yeah, that was it. That was it. Good point. I forgot about that. I completely forgot. Awesome. Good job. And now, yeah, that was awesome. And now let's go back to the full glory of 4,000 pixels. I don't care. Okay, while it builds, let's do some parallelism maybe. Yeah, like working with a low quality image is, I don't know, it doesn't fit my style. Like you can do it, I guess, but I want to see the good stuff. Vector is already doing SIMD. It is, yes. But we're not doing multi-threading. We are doing, look. Well, okay, it doesn't look like we're hammering one specific thread because we are bouncing probably back and forth a little bit. But you see, we're not really making good use of the camera. I think it's thread pull time. I think it's thread pull time. So how do we do this? We couldn't put the thread pull immediately inside render. Maybe this is how we do it. Yeah. Okay. So start the thread pull. So var pull equals std.thread.pull.init. I don't know what the options are. This is fine. Then we need to do. Oh, there we go. That's more like it. There we go. Okay, so what we need to do next is we need to make a function to compute a row, I believe. This needs to become a function, basically. Function compute row, I guess. So for 0.image width, blah, blah, blah. We're missing h, so we need to be given h. We need to be given world. And we need access to out. But do we? No, we can't use out anymore. Now we need to... well, I mean, yeah. Sorry, let me think about it. You can do out, but now out... yeah, how does it work? Let me think about it for a moment. Because we need some... we need some form of ordering. Yeah, binary ppm would help, huh? Binary ppm would help. That is true. We're not looking at it anymore, to be fair. Should we take the jump? Okay, so here's what we're doing. For now, we are doing this. Andrew, do you still have your snippet around? I don't remember. I didn't save it. If you still have it around. Oh, okay. So it's go from P3 to P6, replace prints with write byte. Understood. Okay, I'm going to do that. I don't need the snippet then. Thank you. So for now, we are not going to do any weird transformation. We'll keep this as a function. We call everything as it was before. Let's see if it builds. No, what did we go do wrong? Right. Can return an error. We try. Okay, so we're back to functioning. Then in the meantime, we go here, we say, so it's P6. And then write byte. So you're saying that there's no new lines at all? So we do P6. And then we call write byte for every number. Only chain printing on loop. Okay, so this stuff you're saying then stays as it was. And then this guy prints vector color. That gets me inside alt. color P6, color format P6. Okay, so we didn't break any functionality. Although this is still slow, so let me reduce the size of the image. Um, okay, we migrated to P6 successfully. That's great. So that means that our output, now we know what it is statically. So in camera, here we have the pool. Then we know before the pool, let's do the output buffer. I think we need to put it on a heap. It's probably better for everybody. And we don't have a GPA in here, really? No GPA? We got this far without any kind of heap allocation? Can you imagine? 0 heap allocations. I wonder in comparison how the C++ implementation is doing right now. Let's see. I will have an image in memory array of arrays allocated up front. And then when it's done, dump it into a file. Yeah. So let's see. sd.snp heap. So let's make this our GPA. Const GPA equals heap.smp allocator. Put it here. Then our out buffer is try GPA.alloc. And then we have to alloc. I guess it's a U8. Or do we make it a slice of arrays? I think we should make it a slice of... sorry, the base type should be 3 U8s, I guess. And then we do... how many of those? It's EMG width times EMG height. Here we have the pool. And then when we compute a row, we don't give it out, we give it... actually, we give it the right slice at that point, which is a row, which is then going to be out buff. Oh, you know what? Maybe we can do better than this. Maybe, you know what? This can be a... let me think about it for a moment. No, that works, I think. We give it out buff at EMG, sorry, at H times EMG width dot dot to out buff, just for completeness, is a pointer to... it's a slice to 3 U8s. And this should be then from 0 to EMG width times 3. No, y times 3 because we already have 3 items. So this should be it, I think. Then here we don't have out, but we have our memory. And then blah, 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 blah. We do this stuff. And instead of printing, we do... Oh, fuck. This guy likes to print. We don't have a non-printy way of doing this. I guess we can do this. We can do const w. Let me think about it. Now, you know what? Let's go take the logic because I could make a writer out of it, but it seems too much jank to try and do that when we might just copy the logic from here and call it a day. Why not? Out b equals pixels. No, because we need to apply the gamma transformation, right? I guess we can make this probably. We need to apply the gamma transformation, and then we need to quantize it. So we can't. We basically need to replicate this functionality one way or another. So we can make this pub. So we can apply it. And then we need to do this. And actually, this can be immediately well, I guess out at w equals x, y, z. There we go. So this should work, right? Let's see what problems we have. Unused local variable. Okay, yeah. Let's try this. Let's see if this works without the thread pool. Then we add the thread pool second. Now we are setting it out, and then we just need to print it out. So before we flash, we do try out dot how do we print our bytes now? What's the appropriate way of doing it? Let's see what we have. There's write byte, splat byte, splat bytes, splat bytes all, write slice, swap. I think we want write slice. Oh, write slice endian. Slice as bytes. There we go. And as for Endian, I don't know. What are my options? Big, little. Little. Okay, let's see if this works. Okay, we need to do stuff. 2 gamma is not marked pub. I thought I did. I didn't save. Okay. Okay. Still working. Haven't regressed anything. So you only have 1 byte numbers. True. Um, Okay, so it's time to go thread pool. So we have a thread pool, and then for each one of these guys, we do we pass down also PR, I think. Is this a pointer? No, we pass down a pointer to PR. And in here, we do it here. Perfect. And in here, we instead of doing this, also this does not return an error anymore. It doesn't try to do anything. So remove this. And now we do pool.spawn function arguments work group. Is there no wait method on the pool? Okay, wait. Wait and work. Spawn WG. Let's see, returns func to the thread pool, calling wait group to start beforehand and wait group to finish after it returns. Spawn WG ID, spawn, wait and work. Yeah, I guess we want a wait group because we want to await all of them. Where to get a handle to await group? State, thread reset event, start many, finish, wait, reset is done, spawn manager. The init join. Oh, join is private. Spawn WG returns void once a wait group. We have to make a wait group and then we call spawn WG to spawn stuff in the wait group. Okay. Thread dot work group. I don't know. How do you initialize it? How do you initialize it? Wait, are you saying that there is no wait group? What am I doing? Although, yeah, it is public. Okay, never mind. So we make one. It has its own initialization. Okay. We do spawn WG. First argument. Perfect. Well, I guess this is a try. It's not a try. Okay. And then down here we do WG dot wait start. And WG dot finish. I mean, can we start it here so that we don't have to wait? Let's see the definition. Calling start beforehand and finish after it returns. Oh no, these calls. Okay, wait. How do we then we do something else? It's not start and finish. What do we do? Call wait on it. Okay. Da, 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 da. Can this error out? It cannot error out, so we wait. And wait and work. Wait and work. I don't see wait and work on this guy. Oh, I see. This is so funny. Okay, sure. Wait and work. Why not? While we're waiting, might as well work, right? Okay. This is not the WG, this is pool, right? So pool dot wait and work WG. Okay. Okay, then we write. So this should be it. What's the next problem? Expected to arguments found one in init. What did you want in here? Come on, your definition not found, man. Init pool options. Options. Oh, yeah, you said that it was a pin struct, huh? There we go. I guess we try this init. Yeah. Next problem. Using start field allocator. Oh, there we go. Next problem. Find a const expected progress node. Found const progress node. PR. Oh wait. I guess. Complete one doesn't need a pointer. Okay. Sure. Camera. Go to 4000. There we go. Now we're cruising. Okay. It works. We're cruising. Haha. Nice. Okay. Not bad, I would say. We're getting close to my cutoff point, so I still have energy, so I want to go to keep going forward. But we're getting close to my cutoff point. Let's see how far along we are. We are at 10.6. So we have just one little bit of metal. Then we have Dielectrics. Okay, Schlick approximation. What? Defocus blur, and then we're next. Okay, so we're basically kind of close, but we still have 3 chapters to go through. I'm gonna continue. I'm not committing necessarily to get all the way to the very end, but let's continue a little bit more for sure. Let's see. We can also randomize the reflected direction by using a small sphere and choosing a new endpoint for the array. We'll use a random point from the surface of a sphere centered on the original endpoint, scaled by the fuzz factor. So this was, I guess, this was the original reflection. And then we choose a point, and that moves this here. In any case, this is the stuff that YouTube video description says got a question asking chat, but of course being completely ignored. Please just use an atomic variable to track the current image block. Don't use scan lines and loop until it's out of range. Dude, relax. Okay, relax. The bigger the fuzz sphere, the fuzzier the reflections will be. This suggests adding a fuzziness parameter that is just the radius of the sphere, so 0 is no perturbation. The catch is that for big spheres or grating rays, yeah, sorry, YouTube bugs out on my chat client. I need to fix it. I need to upgrade to the latest. We need to have the new IO stuff, and once we have the new IO stuff, I'm gonna fix Borg for YouTube. Yeah, I don't know what's wrong with the YouTube integration. I have to say the YouTube integration is horrible. So I don't like working on it because the YouTube APIs is disgusting. So yeah. In any case, you know what? Let's do a restart for our friends who are using YouTube. Oh, there we go. Apparently I also got that does not work. Wait. Yeah. Okay. I'm just OMG, just use an atomic counter, please. Relax, man. So let's see. Metal, we're saying, oh, okay, so we're adding fuzziness to the metal. Let's go do that. Objects. Metal, albedo, fuzz. That's another vec3, right? No, it's not a vec3. We said it's just a radius. What is it? Yeah, it's a double. It's just the radius of that sphere, which makes sense. It's like just what we're scaling it with. So F64. And so we're doing random unit times fuzz. So reflect. What was it? Yeah, plus. Back.splat. Metal.fuzz. You know what? We can also do this. Go on a new line after the sum. Times. We said vec.random unit. There we go. Okay, so with this we have also fuzziness. Return. Wait a second. We are returning a Boolean, which is based on whether the dot of the scatter direction and the rect normal is greater than 0. We don't have this. Wait, did we miss something? Okay, so the problem is, since we're adding some randomness, I guess we are now affected here, like in the other one, where no, in this case, it's not even a matter of being near 0. The matter is that we could be somehow so we're doing the dot with the normal, are we? Is it the dot with the normal? Yes. So we're checking again if we're still reflecting outwards, because we might be reflecting inwards. And this could be caused by the fact that this direction could have been changed too much by this. So the idea is we want to do this if vec dot dot direction and h dot hit dot normal, which is n for us, is lower than 0, then we return null. This is how we express this in our case. All these weird side effects are really not helping, in my opinion, in this code snippet. Like the fact that you have these out pointers and you write to them and then you read through them. In any case. Okay, so now what are we doing? Materials left and right, we're giving it some fuzziness. 0.3 and 1, okay? So let's go to main. So this is dot fuzz plus 1. This is dot fuzz equals 0.3, I believe. What did we do wrong? Expected one arguments found 0. Oh, don't tell me. We need to pass random, huh? Don't we? Okay. Do you not unit the first part of the reflection calculation? The book doesn't unit anything. Apparently, no. We don't. I don't know. Yeah, I think we got the solution. So the one to the left does kinda is now it's not as smooth. Well, it's not as perfectly reflective as before. The one to the right has now basically become kinda Lambertian, kinda matte. It's velvet now, kinda. It's not even that. It's like what do you call it? It's like aluminum. It's like one of those Apple product finishes. Yeah, so I think we got this perfectly. Frosted, brushed. Oh, brushed I like. Yeah, I mean, they all make sense. Thank you all. Thank you all. Yeah. Let's see. Clear materials such as water, glass, and diamond are dielectrics. Let's go. We're doing glass. When a light ray hits them, it splits into a reflected ray and a refracted transmitted ray. We'll handle that by randomly choosing between reflection and refraction, only generating one scattered ray per interaction. No, why don't you make both? Actually, wait, isn't it in reality that you kind of have both? I guess it depends on how you want to model it. I don't know how reality actually works. I don't know if people actually know how reality actually works. Never mind. As a quick review of terms, a reflected ray hits a surface and then bounces off. A refracted ray enters it. Yeah. Bends as it transitions from a material surroundings into the material itself, such as a glass of water. And this is why a pencil looks bent when partially inserted in water. Yes. The amount that a reflected ray bends is determined by the refractive index. Generally, this is a single value that describes how much the light bends when entering a material from a vacuum. Glass has a refractive index of something like 1.5 to 1.7. Diamond 2.4 and air is 1.00293. When a transparent material is embedded in a transparent material, you can describe the reflection with a relative refraction index, the refractive index of the object's material divided by the refractive index of the surrounding material. For example, if you want to render a glass ball underwater, then the glass ball would have a refractive index of 1.125, and this is given by 1.5 divided by 1.33. Okay, sounds good. You can find the refractive index of most common materials with a quick internet search. Cool. Refraction. The hardest part to debug is the refracted ray. I usually first just have all the light refract if there is any refraction at all. For this project, I tried to put 2 glass balls in our scene, and I got this. I have not told you how to do this right or wrong yet, but soon. Okay. Is that right? Probably not. Glass balls do look odd in real life. Sure. But no, this isn't right. The world should be flipped upside down and no weird black stuff. I just printed out the ray straight through the middle of the image, and it was clearly wrong. That often does the job. Oh, just printed out the ray straight through the middle. Interesting. Let's see. Refraction is described by Snell's law, where the two Greek symbols that almost look identical are the angles from the normal, and this other weird Greek symbol, pronounced eta and eta prime, are the refractive indices. The geometry is this. I mean, sure. So in order to determine the direction of the refracted ray, we have to solve for sin of Greek symbol. On the refracted side of the surface, there is sorry, theta. Okay, thank you. There is a refracted ray R prime. Where's R prime? It's not in picture. Okay, and a normal N. So I guess this is oh no, a refracted ray. So this is R prime, I guess, and this is the normal. And there exists an angle between them. This angle here, theta prime. We can split R prime into the parts of the ray that are perpendicular to N prime and parallel to N prime. Yeah, so this vector here, and this vector here, like when you split it, sure. Oh god, this is perpendicular and this is parallel. Okay, so R prime is the sum of the perpendicular vector and the parallel vector. Actually, no, wait. Perpendicular vector, parallel vector. This is the norm, the vertical one. Wait, is it actually? The vertical one is the norm, right? Yes. The vertical one is the norm. Okay, so we solve, if we solve for our perpendicular and our parallel, we get this formula. You can go ahead and prove this for yourself if you want, but we will treat it as a fact and move on. The rest of the book will not require you to understand the proof. We know the value for every term on the right hand side except for cosine of theta. It is well known that a dot product of two vectors can be explained in terms of the cosine of the angle between them. Oh god, yeah, this has been a long time since I've done this. Oh, I'm having like flashbacks. If we restrict a and b to be unit vectors, then a times b is cosine of theta. We can now rewrite our prime perpendicular in terms of known quantities. Okay, when we combine them back together, we can write a function to calculate our prime. Okay, so this is the function that calculates refraction. Cool. Back. Reflect. Refract. Okay, so it's a vector UV. Okay, that's the wait, is this the input vector? Because they do that implicitly, right? Well, I mean, this thing has to be a function of your vector, the normal, and the ratio between the two refractive indexes. So yeah. Refraction ratio, I guess. Okay. So const cos theta is at mean between dot of minus v and n and 1.0. Okay. Then const r out perpendicular is refraction ratio times b plus cos theta times n. I think we need to splat some stuff in here. So N is the normal. V is a vector. Guy here needs to be splatted. Splat. Then refraction ratio also needs to be splatted. Okay, and then parallel minus at SQRT of, oh my god, the absolute value of 1 minus R out perpendicular dot magnitude do 2 times N. So we need to splat. Is this right? Magnitude, ABS, SQRT. Yeah. Okay, and N is normal. Okay, so this is refract. Then we create a dielectric material. Okay. Objects. Let's see. I'm gonna copy metal for this. Dielectric refractive index. Although, do we put the index in here or do we put the ratio? I guess we need the ratio against air or something. I don't know. I guess we'll see. Although I guess the air can be approximated to 1. So, well, I guess we'll see. Okay, so we don't reflect, but we refract. And that wants the vector, the normal, and the refraction ratio. So yeah, this scatter needs to know. I guess we have to put here the ratio then. Dielectric. And I think this is where it ends because we don't do any of this, at least for now. I guess viscosity maybe is something that adds some randomness. I don't know. We don't do this because we are not randomizing anything. Let's see what the code here does. Oh, they keep here the index, and then they do 1 over refraction index. Okay, I mean, yeah, sure. Okay, then what do we do? If rec front face Ri is either 1 over refraction index, otherwise is refraction index. Oh. I guess the question is, are we entering or are we exiting the material? That is indeed a good point. the what do we call it in heat? This stuff, it's not face, front face, yeah. So here we do if front face, else and we can do it like this. Also, they call it refraction, refractive, okay. Unidirection and then refracted is unidirection. Oh, we're again ignoring the input ray. Okay. No, never mind. We create a. Okay, no, we're scaling it. Right? We are scaling. What is the word? We're normalizing the this guy. How do we normalize it? What do we have in back? Unit. That's what we do, right? So this is we're doing unit of this guy. Okay. And that's it. And attenuation is color 111. So there's no albedo. Okay. Then we make the material to the left a dielectric. Okay. Let's watch this go out of whack. Refraction index. What do they give it? 1.50. Okay, what's the problem? Oh, yeah, right. Magnitude 2 can't be called that way. Let's zoom back. Which in case is not back at all. Okay. Okay, let's see how it goes. It worked. I think it definitely worked. Yep, we got it. We got it. Because all the rays that go from the left to it, right now, as we're implementing it, they don't reflect at all. They only refract. And so the ones that go straight, they always refract. And so it's basically acting as a lens. Now, how would we add reflection? I know that the book is going to tell me, but I'm curious to try and freestyle it a little bit. So the idea is here we have to choose. Do we want to reflect or refract? So it's a choice that we have to make. Let's make it a 50-50, maybe. I guess this probability probably is something that has to do with the type of material, maybe. So if we reflect instead of refracting, how does it work? Let's see. If rand.bool bool, right? No definition found. Really? Boolean. Oh yeah, of course, because we can't use bool. Okay, if rand.boolean. Actually, can we do enum? I think we can do enum. It's just that it can't be called enum. There's boolean. Yeah, enum value. There we go. And instead of an if, we do a switch. Okay, so in the refract case, that's what we implemented here, basically. And let's put also the returning here. In the case of reflect, how does it work? Well, we do basically a reflection as we were doing it before. So we can actually copy this stuff. So we reflect. What about fuzziness? Let's say that we don't have any fuzziness for now. So we just do reflect on, and that's the direction, blah, blah, blah. And then we have to choose this. And we don't have a color. So let's do vec.1. And then right now we're picking 50-50. Let's see what happens. Also, you know what? We need to worry now about vectors from inside reaching the outside. I don't think we're doing that right. Let's see what happens. Yeah, so there's a little bit of these. We see a little bit of this. What is this that we're seeing here? Yeah, I think this is what I'm talking about. Here we are not realizing that this should not be seen here. We're kind of like reflecting. This guy is being... Oh, you know what? Actually, no, wait a minute. Should the inside reflect this way sometimes? Maybe, I guess, I don't know how physics works. Do you sometimes reflect from the inside instead of refracting towards the outside? Instead of like a glass? I think you do, actually. But let's say that you don't. If you don't, then it's a matter of direction, right? Where you say if you do it like this, I think. If hit dot face front face. I think it's if not front face. Return null. That's right. So let's imagine that glass doesn't do that, but we could each time. So you're saying I'm giving it? I shouldn't give it that high of an attenuation. I should give something different. That's a fair point. Yeah, and this way we don't have the internal reflection anymore. I guess it's time to learn how the world actually works. I don't know. You know what? I'm gonna have a book tell me how the world works. Let's go. Total internal reflection. So one troublesome practical issue with refraction is that there are ray angles for which no solution is possible using Snell's law. When a ray enters a medium of lower index of refraction at a sufficiently glancing angle, it can refract with an angle greater than 90 degrees. If we refer back to Snell's law, the derivation of sin of theta prime. Okay, there's a bunch of math that I'm not following. Let's see, the value, blah, blah, blah. The equality between the two sides of the equation is broken, and the solution cannot exist. If a solution does not exist, the glass cannot refract, and therefore must reflect the ray. Oh, so there is a rule based on when you reflect and when you refract, and it's not at random, turns out. That makes sense. Let's see. If Ri times sin theta is greater than 1.0, must reflect, otherwise must refract. Okay, so instead of randomizing the choice, so we can do it like this: const outcome is an enum refract, and it's based on if with formula Ri times sin theta. So we need Ri. Ri was the ratio, I believe. So we need to compute the ratio no matter what. And the outcome is if ratio greater than what was it, 1? Oh, times sin theta. Where the heck is sin theta? We don't have it here. Oh, God. Okay, so where's sin theta? Where do I get sin theta? Oh, it's a constant. Well, guess what? Guess what? Okay, let's see. Cos theta. This is. Oh, these are based on. Okay, so these have to be computed at runtime. Okay, cool. At mean between vec dot dot minus unit direction vec dot unit direction. Wait a second. Unit direction. Oh, is what we compute down here. Okay. K dot n. Unit. Wait, what's happening here? Unit direction. Oh my god, something bad happened. Never mind. Okay, I'm starting to lose steam. That's why I think there's something to become weird. Okay, so we do this. What if I add a comma in here? Will this make it any better? Actually, yes. This is not bad. So then we switch on the outcome, reflect or refract. And I haven't checked how we reflect. So you do this. Oh, and then bool cannot refract. If cannot refract, Ri times sin theta greater than 1.0. Let's see. Ratio times sin theta greater than 1.0. Then we do reflect, otherwise refract. Okay. It's just a simple reflect, otherwise a simple refract. Let's see if yeah, it's actually very simple. Yeah, just a reflect. So this face stuff I made up. This part we don't need. Okay. Let's see. Attenuation is always 1. The glass surface absorbs nothing in both situations. Interesting. If you enter prior scene, nothing has changed. With the new dielectric scatter fraction, we'll see no change, huh? Yeah, wait a second, dude. What happened? Wait a second. What happened? So we never end up in the reflect case. How do we never end up in the reflect case? Well, it turns out that a given sphere of material with an index of refraction greater than air, there is no incident angle that will yield total internal reflection. Neither at the ray sphere entrance point nor at the ray exit. This is due to the geometry of spheres. It's a grazing incoming ray will always be bent to a smaller angle and then bent back to the original angle on exit. So let's see. So we can now how can we illustrate total internal reflection? Well, if the sphere has an index of reflection less than the medium is in, then we can hit it with a shallow grazing angles, getting total external reflection. That should be good enough to observe the effect. So, okay, so we change it as if it were like a ball of glass inside water, and it's gonna make it like a metal at that point. So we're doing left dielectric. We're doing 1.0 over, what was it, 1.3? 0.33, okay. 233. Yeah, and it's just gonna be basically metal. Why metal? I don't know. Let's take a look, but I'm assuming that it reflects everything or not. This is weird. Wait, this is not how stuff works. What's going on? Or maybe it is. Wait a second. Although, no, wait, what is this thing here? Okay, let me think about it. So what's happening is, no, it actually kind of works. So the idea is, it's still glass. You're right. It's not something that is completely reflective from all angles, but it is reflective a lot. I guess it's like a bubble. Maybe, okay. I don't know exactly what the correct analogy would be, but so it's reflecting this guy on this side. Then we get to a point where we stop reflecting and we start refracting, and so we enter inside. So I guess this is not really that there's something specific. It's just like the point where the angle changes of a rays or something. I don't know. Let's see what it's supposed to be. Yeah, it's supposed to be like this. Air bubble sometimes refracts, sometimes reflects. Yeah. Left sphere is an air bubble in water. Okay, so this is the analogy. An air bubble in water. Okay, we got it. Schlick approximation. Now, real glass has reflectivity that varies with angle. Look at a window at a step angle, yes, and it becomes a mirror. Yes, there is a big ugly equation for that. But almost anybody uses a cheap and surprisingly accurate polynomial approximation by Christoph Schlick. Very Schlick, Christoph. Or I should say Christoph. I don't know. In any case, this yields our full glass material. Let's see. If cannot refract, or reflectance. So that's why they put it in a separate variable. Okay. Let's do it as well. Static double reflectance greater than random double. What? This is still randomized? If reflectance cos theta Ri is greater than a random double. So I guess it's something like as you're approaching the limit, you start reflecting more and more. I'm gonna say Schlick. Wait, no, this is just a literal random double. This is rand dot float. The ray kind of splits, but you're approximating it just by sending a lot of rays to it. It seemed like the ray was splitted. Yes, that makes sense. And now we need reflectance, which we can implement inside Dielectric, which is the right place where to put it. But that's nice. God damn it. R0 is this, and then we modify it. Fine var. Then we return R0 plus 1 minus R0 times std pow. We have it pow. We don't, do we? No, we don't. std.math.pow. God damn it, I can't even type it. Type F64. Wait, what is the problem? Expect a comma after field. What have I done? This is a function. This is the struct. Struct should end with a comma, actually. Why is there this? Copy pasted it. Yeah, okay. Perfect. Okay, does it work? Modeling a hollow glass sphere. Let's model a hollow glass sphere. This is a sphere of some thickness with another sphere of air inside of it. Oh, Jesus. If you think about the path of a ray going through such an object, it will hit the outer sphere, refract, hit the inner sphere. I guess we do it by literally placing a sphere inside another sphere. Oh, we did it. I think we did it, right? It works. Like the book doesn't seem to show anything, but we have... This has changed. It's less like of a instant change and more like a thing where things start to change. The book doesn't show anything. Okay. Let's see, the outer sphere is just modeled as a standard glass sphere with a refractive index of around 1.50. The inner sphere is a bit different because its refractive index should be relative to the material surrounding the outer sphere. Yeah, So yeah, you're not really putting there their indices. You're putting there their ratio. Yeah, because there's no concept of what you're immersed in. Yeah, that makes sense. Okay, so we make another sphere. We need a material bubble and a material left. Okay. So this is the bubble. And this is the glass left. I don't know what to call it. And glass is 1.5. Okay, so we have an extra sphere. What is it? -1, 0, -1, -1, 0, -1, 0.4. Right, slightly smaller radio. And this one is glass left. Okay. So the result looks a lot like what we had earlier. I guess it's except that the sphere in the middle is like more pronounced than what we just saw. Wait, is this actually correct? No, I think I think we flipped them around. A hollow glass sphere. Wait, something went out of whack, I think. Oh, the smaller one is bubble. The outer one is glass. We made something weird. Okay. Positionable camera. Okay. Cameras like the Dielectrics are a pain to debug, so I always develop mine incrementally. First, let's allow for an adjustable field of view, the FOV. This is the visual angle from edge to edge of the rendered image. Since our image is not square, oh, there we go. Although, wait, this does not look like this entirely either. There's it kind of does, but this is slightly different. Why do we not have this here? We're messing something up. Did I mess up the sphere dimensions? Let's see. They are both at the same position, slightly different radius. Glass left is 1.5. And the other one, the other one is 1 over 1.5, not whatever it was before. Which makes sense because its ratio needs to be, well, whatever its own ratio should be over what's outside. And the outside is 1.5. So if we use something different, then yeah, the math goes a little bit out of whack. Let's see. Since our image is not square, the FOV is different horizontally and vertically. I always use vertical FOV. I also usually, there we go. Now we got it. Yeah, this is exactly what we were supposed to get. Okay. This is the visual angle from edge to edge to the render image. Sorry, blah, 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 matter of personal taste. I also usually specify it in degrees and change to radians inside the constructor, a matter of personal taste. First, we'll keep the rays coming from the origin and heading to z-1 plane. We could make the z-2, make it the z-2 plane or whatever, as long as we make it as long as we make h a ratio to that distance. Here's the setup. You know what? I'm starting to feel that maybe this might be more enjoyable if I take a break and we do this in one final session tomorrow. I guess on one end, you could say it's a failure. It wasn't in a weekend. But also, you know what? The problem is that I have this like weird restriction where if I want for people in the US to join, then I have to wait 6 p.m. my time, and that leaves me not a ton of time. Yeah, I know. How's tomorrow not a weekend? What do you mean? So I'm gonna take a break, I think. This was fun though. This was cool. I got not all of it, but a good chunk of it, I feel like. It was nice also ad-libbing the final part. Tomorrow is Sunday. No, today is Sunday, at least on my side of the planet. Okay, so so yeah, I think we're gonna stop here. But this was awesome, and yeah, we made a ton of progress. It's been fun. Things mostly worked first try. Not everything every time worked first try, but close enough. We can get the 4,000 pixels. I'm gonna call it the 4K. We can get the 4K resolution computed actually fairly quickly. We can enjoy all the reflectants, and whatnot. I'm joking, but like we can enjoy glass spheres also with the weird reflections that I'm not sure I am even able to appreciate in real life. And yeah, this was nice. So I'm gonna stop here, and tomorrow 6 p.m. usual time we do the final section where we, I don't know, play around with the camera or whatever else is left. Thank you all, and I'm gonna stop the recording here.